Donuts, brownies, and muffins are built to look perfect and taste identical at full production speed. Inside industrial bakeries, batter is mixed to exact viscosity. Donut rings are cut or deposited in flawless shapes. Trays of brownie mix are leveled for even thickness, and muffin cups are filled with precision dosing. In this video, we follow the line from bulk ingredients to fryers and tunnel ovens, revealing how proofing and high-speed packaging lock in that fresh texture every time. Donuts are manufactured by creating a dough or batter with controlled aeration, shaping it into rings or filled shells, setting structure by frying, then applying glaze or coatings before cooling and packaging. Production begins with ingredient conditioning because dough rheology and fermentation behavior depend on temperature and hydration. Flour is sieved to remove lumps and to improve flow into the mixer. Sugar is screened to control crystal size and reduce dust. Salt and leavening are weighed precisely because they affect gas generation and gluten behavior. Fats are tempered to a plastic consistency so they disperse evenly. Eggs or dairy liquids are tempered to avoid shocking the dough temperature. Water temperature is used as a control lever to hit a target final dough temperature. Two main donut types drive different front-end processes. Yeast-raised donuts use a developed dough that ferments and expands. Cake donuts use a batter that is chemically leavened and deposited directly into oil. Many factories run both types on separate lines because the mixing and shaping equipment differs. For yeast-raised donuts, mixing begins with combining flour, sugar, salt, yeast, and a portion of water. The mixer starts at low speed to hydrate flour without throwing dust. After hydration, the mixer increases speed to develop gluten. Gluten development creates an elastic network that traps fermentation gas. Mixing time is controlled because underdevelopment yields weak dough that collapses. Overdevelopment yields tight dough that resists expansion and produces a tough bite. Fat is added after initial gluten has formed. Adding fat too early coats flour and slows gluten formation. Adding it later allows gluten to develop and then softens the network. Eggs and dairy can be added with fat or in a separate step depending on formulation. The dough is mixed until it reaches a defined elasticity and smoothness. Temperature is monitored because friction heats the dough. The target is a final dough temperature that supports consistent fermentation rate. Once mixed, the dough enters a bulk rest stage. Rest allows flour hydration to continue and lets the gluten relax. Relaxation improves machinability and reduces shrink after shaping. For yeast donuts, the rest is also a fermentation stage. Yeast consumes available sugars and produces carbon dioxide. Gas inflates small cells within the dough. Time and temperature determine how much gas is produced and how the flavor develops. After bulk rest, the dough is divided and sheeted. Dividing ensures each downstream piece has consistent mass. The divider cuts dough into chunks that feed a sheeter. The sheeter reduces thickness through a series of rollers. Roller gaps are adjusted to avoid tearing. As the sheet thins, the dough becomes smoother and more uniform. A gauging stage locks thickness so ring cutters can produce consistent weight. Cutting forms the donut shapes. A rotary cutter punches rings by cutting an outer circle and removing a center plug. The plugs can be routed to other products. Cutter sharpness is important because dull cutters seal poorly and create ragged edges. Ragged edges absorb more oil and fry unevenly. The cut rings are transferred to proofing trays or conveyors. Proofing is a controlled fermentation stage that expands the rings to near final size. Rings sit in a warm, humid environment so surface does not dry out. Humidity prevents skin formation, which would restrict expansion. Temperature controls yeast activity. Proof time sets final volume and cell structure. Underproof yields dense donuts. Overproof yields fragile donuts that collapse when moved. Cake donut production uses a different approach. The batter is mixed with minimal gluten development. Dry ingredients such as flour, sugar, salt, and leavening are blended first for uniform distribution. Liquid ingredients such as eggs, milk, and melted fat are mixed separately. The two streams are combined and mixed briefly. Mixing is controlled because excessive mixing develops gluten and makes cake donuts tough. The batter must remain smooth and aerated with small bubbles. Cake donut batter is portioned by a depositor. The depositor uses a plunger or gear pump to meter batter into shaped rings. A nozzle or cutter forms the center hole as batter enters the oil. Deposit timing controls weight. Viscosity control is critical because thin batter spreads and produces misshapes. Thick batter produces rough surfaces and poor internal expansion. Batter temperature is therefore controlled to maintain consistent flow. Frying is the main setting step for both types. Donuts enter a fryer filled with hot oil. Oil temperature is held within a narrow band because it controls crust formation and oil uptake. When donuts enter the oil, the surface water flashes to steam. Steam creates outward pressure that expands the structure and prevents excessive oil penetration during the initial phase. Starches gelatinize at the surface and form a crust. Proteins coagulate and lock the structure. Yeast-raised rings typically float and fry on one side first. A conveyor guides them through the oil. After a defined time, the rings are flipped. Flipping ensures both sides brown evenly and the internal structure sets symmetrically. Flip timing is critical because early flipping can collapse one side. Late flipping can create a thick crust on the first side. The flip mechanism uses paddles or rotating bars, synchronized with belt speed. Cake donuts are often flipped as well, but their timing differs because they set faster. Their batter structure forms quickly due to chemical leavening and rapid heat penetration. The fryer profile is tuned to develop a smooth crust without excessive cracking. Cracking can occur when gas expands too quickly under a rigid surface. Temperature and residence time are adjusted to balance expansion and crust set. Oil management matters because crumbs and batter fragments burn and darken the oil. Filtration removes fines continuously. Oil turnover maintains quality and stable heat transfer. Circulation keeps oil temperature uniform across the fryer. Uniform temperature prevents color striping where one lane browns more. After frying donuts, exit onto a de-oiling conveyor. Vibration and drainage remove surface oil. Air blowers can strip oil from creases. Removing surface oil improves eating quality and reduces greasy coating issues. It also improves glaze, adhesion, because oil films interfere with sugar glaze wetting. Cooling begins immediately after frying. Donuts must cool to a coating temperature window. If coated too hot, glaze becomes too thin and runs off. If coated too cool, glaze sets too fast and produces uneven coverage. Cooling conveyors use controlled airflow. Cooling also allows internal moisture to redistribute. This redistribution affects softness and shelf texture. Glazing is applied by dipping or curtain coating. A glaze is a sugar syrup or icing with controlled solids. Solids level sets thickness and set time. The glaze is mixed to remove lumps and held at a stable temperature. Donuts pass under a glaze waterfall or are inverted and dipped. Excess glaze drains off. A short setting conveyor allows the glaze to crystallize into a smooth finish. For powdered sugar, finishes donuts are coated while slightly warm, so powder adheres. A tumbler or shower deposits powder. Excess powder is recovered by screens. For cinnamon, sugar finishes. The coating is applied in a rotating drum where sugar and spice blend contacts the surface. Surface condition must be slightly tacky for good adhesion. Filled donuts add an injection step. The donut is fried as a shell without a center hole, or it is cut to allow filling. filling is prepared as a pumpable cream or jam with controlled viscosity. A multi-needle injector inserts needles into the donut and pumps a measured dose. Dose accuracy matters because it affects weight and bite. Injection timing must match donut firmness to avoid blowouts. Toppings can be applied after glaze while the surface is still tacky. Sprinkles, nuts, or crumb toppings are dosed through spreaders. Adhesion depends on glaze set time. If applied too early, toppings sink. If too late, toppings bounce off. A short conveyor section is used as a timing buffer, so toppings land at the right tack level. After finishing the donuts, enter a final cooling and setting stage. This stage stabilizes glaze and fills. It also reduces condensation risk in packaging. Air temperature and humidity are controlled because donuts are moisture sensitive. Too dry air can dry the surface and harden texture. Too humid air can soften glaze and increase stickiness. Packaging depends on whether the product targets freshness for short distribution or shelf stability for longer distribution. Fresh style donuts are often packed in cartons with minimal barrier. The focus is protecting shape and glaze. Cartons are erected and donuts are placed in cavities or on trays. For wrapped donuts, barrier film is used to slow moisture loss and maintain softness. Flow wrappers seal individual donuts or pairs. Seal timing must avoid smearing glaze. Brownies are manufactured by building a high solids batter with controlled aeration, depositing it into trays at uniform depth, baking to a precise moisture endpoint, then cooling and cutting so the interior stays dense while the top stays set and crackled when required. Production starts with ingredient conditioning because brownie texture is sensitive to temperature and particle size. Flour is sieved to remove lumps and to improve even hydration. Cocoa powder is sifted because it compacts and forms clods that create dark pockets. Sugar is screened to control crystal size and reduce dust that can throw off weighing. Fats such as butter or vegetable oil are tempered so they flow predictably. Eggs or liquid egg products are tempered so they emulsify without curdling. Chocolate pieces or chips are stored cool so they hold shape during mixing and do not melt into streaks unless that is the target style. Dry ingredients are often pre-blended to improve distribution and reduce mixer time. Flour, cocoa, salt, and leavening, if used, are mixed gently in a dry blender. Pre-blending prevents localized clumps once liquids are introduced. Many brownie formulas use little or no chemical leavening because the desired crumb is dense. When leavening is used, it is dosed precisely because small changes shift height and chew. The liquid phase is prepared separately because it controls emulsion stability. Fats are melted to a controlled temperature that is warm enough to dissolve sugar partially, yet not so hot that eggs cook on contact. If the formula includes melted chocolate, it is melted and held at a stable temperature. Syrups can be staged to adjust moisture and chew. Flavor additions, such as vanilla, are prepared for later addition to protect aroma. Mixing begins by creating a sugar-fat system. Sugar is combined with melted fat and mixed until the crystals are evenly wetted. Some mixing strategies aim to dissolve part of the sugar to create a glossy top. Partial dissolution influences the classic crackle. The mixture is warmed and mixed enough to reduce graininess, but not so much that it becomes fully dissolved and thin. Eggs are added next, and the addition rate is controlled. Eggs are introduced in portions so they emulsify smoothly into the fat phase. Mixing speed increases during egg addition to create a stable emulsion. This emulsion is the base that holds cocoa particles and flour later. Mixing also incorporates a controlled amount of air. Too much air yields a cackier brownie. Too little air yields a very heavy block. The target is minimal to moderate aeration depending on product style. If the product uses a whipped sugar egg method, the sequence changes. eggs and sugar are whipped first to incorporate more air and dissolve sugar. Melted fat and chocolate are then folded in. This method yields a lighter structure and a higher crackle top. For dense fudgy brownies, the fat sugar first method is more common because it limits aeration and increases richness. Once the wet base is uniform, the dry premix is added. Dry ingredients enter gradually to avoid lumps. Mixing energy is reduced during flour addition to limit gluten development. Excess gluten makes brownies tough and bread-like. The endpoint is a smooth, thick batter with no visible flour pockets. Batter viscosity is monitored because it affects deposition and final height. Chocolate chips, nuts, or other inclusions are added at the end. Inclusions are folded in at low speed so they distribute without breaking. Distribution uniformity matters for visual appearance and bite. If inclusions are fragile, such as cookie pieces, they are added last and mixed briefly. If inclusions are heavy, they can settle in the hopper, so the line may use agitation in the depositor feed. Batter temperature is controlled tightly before deposition. Warm batter flows easily and levels in pans but can cause inclusions to sink. Cool batter holds inclusions in suspension but can trap air and create uneven surfaces. The process targets a temperature that supports consistent flow and even leveling. Depositing converts bulk batter into uniform slabs in trays. A depositor uses pistons or pumps to meter a defined mass into each tray. Depositor heads can fill as a continuous ribbon or as multiple streams that merge. The tray moves under the head at a controlled speed so depth becomes uniform. Leveling knives can smooth the surface. Uniform depth is critical because bake time depends on thickness. For sheet production, the batter is deposited onto a moving oven band with side rails. The band carries the batter through the oven as a continuous sheet. Thickness is controlled by a spreading bar and side rail height. This method supports high throughput and consistent cuts. For pan brownies, trays are filled and then conveyed into the oven. Before baking, some products receive top additions. Extra chips or nuts can be sprinkled onto the surface. Application happens immediately after deposit while the surface is still wet. Spreader systems meter toppings evenly across the width. Topping density is controlled because it affects heat transfer and browning. Baking is the setting step that defines final moisture and crumb. Brownies enter a tunnel oven with staged zones. Early heat raises batter temperature and melts remaining fat. Proteins begin to coagulate and the emulsion thickens. Starch in flour begins to gelatinize as water heats. Gas expansion is limited compared with cakes, but some expansion occurs from trapped air and from steam. The surface begins to form a skin. As baking continues, the top sets and can develop the classic crackle. Crackle formation depends on surface sugar concentration and drying rate. As the surface dries, a thin, brittle film forms. Internal expansion and moisture movement then fractures the film into a crackled pattern. Oven humidity and top heat intensity influence this. Too dry too early can create a hard crust that separates. Too moist can prevent crackle and yield a smooth top. The interior sets later than the top. The target endpoint for brownies is often defined by internal temperature and residual moisture rather than by complete dryness. For fudgy brownies, baking stops while the center still retains significant moisture. For cake-style brownies, baking continues longer to reduce moisture and increase crumb firmness. The oven profile is tuned to reach the desired moisture gradient without burning edges. Edge behavior is a major control point in tray baking. Metal trays conduct heat quickly at edges, which can overbake perimeter zones. Ovens can compensate by controlling airflow and zone temperatures. Some lines use insulated trays or specific tray materials to reduce edge overbake. Uniform thickness and consistent tray loading also reduce variation. After baking, the brownie slab exits the oven and is still soft. Cooling begins immediately to stabilize the structure. cooling must be staged because rapid cooling can cause cracking and can pull the top away from the interior. Airflow is controlled and often dehumidified to avoid condensation. As the slab cools, fats crystallize and firmness increases. Moisture redistributes from the center toward the edges, which can change perceived fudginess. For some products, a post-bake resting stage is used before cutting. Resting allows the slab to equilibrate and become more cut stable. Cutting too hot causes smearing and ragged edges. Cutting too cold can cause cracking in the top. The process targets a cut temperature window where the slab is firm yet still pliable. Demolding or release happens after initial cooling for tray brownies. The slab can be loosened mechanically or released by inverting the tray. Release aids can be used in trays, but the main process goal is clean release without tearing the bottom. For band-baked sheets, the slab continues on the band into a cooling conveyor and then transfers to cutting. Cutting is done with guillotine blades or rotary knives. The first cut trims edges if edge texture differs from the center. Trim can be collected for rework depending on recipe. The slab then passes through a longitudinal cutter that creates strips. A cross cutter then creates squares. Blade, sharpness, and speed are tuned to slice through inclusions without dragging. Cutting can use ultrasonic blades for clean cuts through sticky interiors. Ultrasonic vibration reduces smearing and keeps edges sharp. Portion control is verified by weight checks. Dimensional checks ensure consistent size. Vision systems can detect missing toppings or cracked tops. Broken pieces can be diverted. Crumb collection systems reduce loose particles that would contaminate packaging seals. If the product receives icing or drizzle, this step usually occurs after cutting. Icing is prepared as a sugar fat or sugar water system with controlled viscosity. It is applied by enrobing or by stripe depositing. Coatings are then set in a cooling tunnel. Coating application must avoid overheating the brownie because heat can melt the interior and change texture. Packaging is designed around moisture retention and protection of the top surface. Brownies are moisture sensitive and can dry out quickly. Barrier. Films are used to limit water vapor loss. Individual flow wrapping is common because it locks moisture in each piece. Flow wrappers form film around the brownie and seal it. Seal temperature and dwell are controlled, so seals are strong without melting the brownie surface. Muffins are manufactured by building a batter with controlled viscosity and aeration, depositing it into cups at uniform fill weight, baking to set a stable crumb while retaining moisture, then cooling and packaging to preserve softness. Production begins with ingredient conditioning because muffin batter responds strongly to temperature and particle size. Flour is sieved to remove lumps and to aerate it for consistent hydration. Sugar is screened to control crystal size and reduce dust. Leavening is weighed precisely because it drives rise and internal cell structure. Salt is blended with dry ingredients for uniform distribution. Fats are prepared according to formula. Liquid oils are held at a stable temperature. Solid fats are tempered to a plastic state if creaming is used. Eggs or liquid egg products are tempered so they emulsify smoothly. Milk or water is tempered because cold liquids thicken batter and warm liquids thin it. Dry ingredients are often pre-blended before entering the main mixer. Flour, sugar, leavening, salt, and spices are mixed gently to disperse leavening evenly. Even dispersion prevents tunnels and uneven rise. Cocoa powder or milk powder are sifted into the dry blend when used. Pre-blending reduces mixer time and limits gluten development later. The liquid phase is prepared separately for many muffin lines. Eggs, milk, water, oil, and flavor extracts are combined in a liquid tank with agitation. This creates a uniform liquid feed so the main mixer sees a stable stream. If the recipe uses melted butter, it is blended into the liquid phase at controlled temperature. If the recipe uses emulsifiers, they are dissolved into the liquid phase so they can stabilize the batter during mixing. Mixing strategy depends on the desired crumb. Many commercial muffins use the muffin method, which limits gluten formation. Dry blend is loaded into the mixer, and the liquid blend is added in a controlled pour. The mixer runs at low speed at first, so dry particles hydrate without throwing flour dust. After initial wetting, the mixer increases speed briefly to remove lumps. Mixing time is kept short because extended mixing develops gluten and produces tough muffins with peaked tops. The target is a batter that is smooth but still short. If a cream-style muffin is desired, the process begins with creaming fat and sugar. Creaming traps air and creates a lighter crumb. Eggs are added gradually to maintain an emulsion. Dry ingredients and liquids are then alternated into the mixer. This approach yields more aeration but requires tighter control to prevent curdling. Many high-throughput lines prefer the simpler one-stage method because it is more robust. Batter temperature is monitored continuously. Temperature affects viscosity, which affects depositor accuracy and cell structure. Warm batter flows easily and levels in cups, but can allow bubbles to rise and escape. Cold batter is thicker and can trap air pockets that create voids. The line targets a narrow temperature window that supports consistent deposition and rise. Inclusions are added at a defined point in the mix. Blueberries, chocolate chips, nuts, or fruit pieces are folded in at low speed near the end. Folding limits breakage and prevents color bleed from fruit. Inclusions are staged at controlled temperature because warm chips can smear and cold frozen fruit can thicken batter locally. Distribution uniformity is important because each muffin must have a consistent inclusion count and weight. Once mixed, the batter is transferred to a hopper that feeds depositors. Transfer is designed to prevent segregation. Heavy inclusions can settle if the batter sits too long. Hoppers therefore use gentle agitation or recirculation to maintain uniformity. Agitation must be gentle because excessive shear can deflate batter and change rise. The depositor feed lines are designed with smooth bends to avoid trapping inclusions. Depositing places batter into paper cups or directly into trays. Cups are first placed into pans or carriers that support them in the oven. A cup denister separates cups and places them accurately. The depositor then meters batter by piston or by volumetric valve. Fill weight is controlled tightly because weight drives final height and bake time. Depositor nozzles are designed to handle inclusions without clogging. The deposit pattern can be centered or can be slightly offset depending on how the muffin crowns. After deposition, some products receive a top garnish. Sugar crystals, streusel, or extra chips can be applied to the wet surface. Garnish dosing is controlled by vibratory feeders. Timing matters because the batter surface begins to skin if it sits. Garnish is applied quickly so it adheres before baking sets the top. Trays then enter the oven. Muffins are baked in tunnel ovens or rack ovens. Industrial lines often use tunnel ovens for continuous flow. The oven profile is zoned to control rise and crust. Early zones apply strong heat, so gases expand and leavening reacts. Steam forms from batter water and inflates air cells. The batter viscosity rises as proteins begin to coagulate and starch gelatinizes. This sets the cell walls so the muffin holds its expanded shape. Leavening behavior is controlled by temperature ramp. Baking powder releases gas in stages, and baking soda releases gas based on acid availability. The profile must allow gas release before the crumb sets fully. If the crumb sets too early, the muffin is dense. If gas release continues after the crumb sets, the structure can tear and form tunnels. Zone temperatures are therefore tuned to coordinate gas generation and setting. As baking continues, the top forms a crust and the crown develops. The crown forms because the surface sets while the interior continues expanding. The interior pushes upward and creates the dome top. Batter viscosity and fill level influence crown height. A thinner batter spreads and forms a wider crown. A thicker batter forms a taller crown with sharper edges. Moisture management is central to muffin texture. Muffins need a set crumb that still retains moisture. Overbaking drives moisture too low and yields dry muffins. Underbaking leaves a gummy center that collapses during cooling. The bake endpoint is measured by internal temperature and by moisture loss. Oven airflow and humidity also influence moisture loss. Strong airflow dries the surface faster and yields a thicker crust. Lower airflow yields a softer crust. Color development occurs through browning reactions. Sugar and proteins react at the surface as it dries. Oven top heat influences crust color. Too much top heat darkens the crown before the center is set. 2. Little top heat yields pale muffins. Balanced heat gives even color with a soft crust. After baking, muffins exit the oven and enter cooling. They are still fragile because the crumb is hot and steam-filled. Cooling allows the structure to stabilize. As temperature drops, steam condenses and moisture redistributes. Fats resolidify and the crumb firms. Cooling must be controlled because rapid cooling can create shrink and wrinkling. Slow cooling can allow excessive moisture condensation in packaging areas. Cooling conveyors provide airflow across the muffins. Air temperature and humidity are controlled. Dehumidified air helps prevent surface stickiness. The goal is to bring muffins to a packaging temperature that avoids condensation inside packs. Muffins that are packed too warm release moisture into the headspace and soften the crust. Muffins that are packed too cool can be brittle and can crack at the crown. It all begins, unsurprisingly, with flour. Krispy Kreme uses a proprietary blend of enriched wheat flour, one formulated specifically for its lightness, protein balance, and ability to yield that signature fluffy bite. The flour is sourced from select mills that maintain tight quality control standards, ensuring the particle size, protein content, and gluten strength all fall within strict tolerances. Once delivered to the facility, the flour is stored in stainless steel silos under controlled temperature and humidity, preventing clumping and spoilage. Next, there's yeast, the biological engine behind the dough's rise. Krispy Kreme uses a commercial strain of baker's yeast known for its rapid activation, consistent fermentation profile, and neutral flavor. The yeast is usually delivered in refrigerated blocks or vacuum-sealed pouches to ensure maximum viability. Alongside the yeast, the other raw ingredients include non-fat dry milk powder, high-stability vegetable shortening, dextrose, salt, and water. Each of these ingredients plays a crucial role in shaping the final taste and texture of the donut. The shortening provides mouthfeel and moisture retention, while the dry milk lends a creamy undertone and enhances browning during frying. In the mixing phase, the ingredients are loaded into a spiral or planetary industrial mixer. The water is typically warmed to around 95 to 105 degrees Celsius before being introduced to activate the yeast. The mixer operates on a timed cycle, first gently combining the dry and wet components, then increasing speed to develop gluten and build dough structure. The dough is mixed until it achieves a smooth, elastic consistency with careful monitoring of temperature and hydration levels. If the dough becomes too warm, it risks overproofing, too cold, and fermentation is delayed. Sensors in the mixing bowl monitor the dough's internal temperature, moisture content, and even CO2 output to ensure consistency. Once the dough is formed, it enters the bulk fermentation phase. Giant stainless steel troughs, called dough rests, hold the dough as it ferments for the first time. During this period, the yeast metabolizes sugars and starches, producing carbon dioxide and ethanol. This expands the dough and begins developing its light, spongy structure. Krispy Kreme controls this step precisely, maintaining a temperature of around 80 degrees and 85% relative humidity in the proofing room. The dough rests here for approximately 30 to 40 minutes, depending on the batch size and ambient conditions. After bulk fermentation, the dough is transferred to a sheeting system. This is where things start to get visually impressive. The dough is rolled and flattened by calibrated rollers until it reaches a uniform thickness, typically between 10 to 12 millimeters. From here, it enters the cutting stage. A rotary die cutter stamps out perfect donut rings and holes in a continuous, automated process. The cutting dies are precision machined from stainless steel to ensure sharp, clean cuts and minimal dough waste. Any scrap dough is immediately collected by conveyors and reintroduced into the mixing system for reuse. Each donut ring now travels along a conveyor to the second proofing chamber, essentially a gigantic, climate-controlled cabinet lined with slow-moving racks. Inside, the donuts undergo their final proof, where they double in size due to continued yeast activity. The environment here is tightly regulated, around 90 degrees here and nearly 85% humidity. This proofing process typically lasts 30 minutes, but sensors embedded in the chamber walls adjust for ambient shifts in temperature or humidity, ensuring each donut achieves the perfect rise. Now comes one of the most mesmerizing parts of the process, the fry line. The fully proofed donuts are gently deposited into a continuous flow fryer using an overhead lifting mechanism that preserves their delicate structure. The frying oil, usually a high stability palm or soybean blend, is maintained at a precise temperature of approximately 365 degrees. Each donut floats along the surface, first frying one side, then automatically flipping at the midpoint using a mechanical turner. This results in the even golden brown exterior Krispy Kreme is known for, with a pale proof line around the center indicating proper fermentation. The frying process takes just under a minute per side, and the timing is crucial. Over-frying results in a dense, oily product. Under-frying leaves it doughy and structurally unsound. Oil filtration systems continuously clean and circulate the frying oil, removing carbonized particles and extending the oil's life while maintaining food safety. Once the donuts exit the fryer, they move onto a draining conveyor where excess oil drips away. The donuts are now fully cooked, but they're still bare, until they pass through the glaze waterfall. This is the stage most visitors at Krispy Kreme stores eagerly watch through the viewing window. The glaze itself is a proprietary blend of confectioner's sugar, water, and stabilizers, mixed in large heated vats to maintain fluidity. It's heated to a precise temperature to ensure it flows evenly over the donuts without soaking them. As the donuts travel beneath the waterfall, a curtain of glaze coats their entire surface in one smooth motion. The donuts continue to move along the belt for several feet to allow the glaze to set. During this time, cooling fans blow across the surface to speed up the crystallization process, giving the glaze its characteristic sheen and snap. At this stage, the original glazed donuts are complete, but not all donuts stop here. Many are diverted down alternate lines for filling, topping, or decoration. Filled varieties like custard, jelly, or cream-filled donuts are processed using pneumatic injection stations. The donuts are gripped and punctured automatically, and then a precise quantity of filling is injected into each center using calibrated nozzles. Topping lines include various enrobing stations for chocolate dips, icing drizzles, and even cookie crumb coatings, depending on the product line. Once decorated, the donuts pass through a final quality control checkpoint. Here, high-speed cameras, sensors, and human inspectors work in tandem to identify deformities, glaze coverage issues, or structural flaws. Any donut that doesn't meet the company's stringent standards is diverted and discarded or sent for animal feed, depending on local regulations. Now comes the packaging process. Original glazed donuts are usually arranged by robotic arms into branded trays or boxes, depending on the sales channel, whether destined for in-store display, grocery retail, or food service distribution. Boxes are barcoded, date-stamped, and sealed automatically. For freshness, Krispy Kreme relies on just-in-time manufacturing. Many facilities bake and ship multiple times per day, with some outlets even co-located within the production plant itself to reduce handling and delay. For external distribution, the boxed donuts are loaded into climate-controlled trucks equipped with racking systems that prevent damage during transit. These trucks make scheduled routes to retail locations, grocery partners, and kiosk outlets, often arriving just hours after the donuts were made. Once on site, employees stock the shelves or display racks, ensuring the donuts are sold within their optimal freshness window, typically less than 24 hours. Meanwhile, any donuts not sold by the end of the day are generally removed to preserve Krispy Kreme's reputation for freshness. In some regions, unsold inventory is donated to food banks or repurposed, while others adhere to strict disposal policies. Throughout this entire process, automation and precision engineering play a central role. From programmable logic controllers managing the mixing and proofing cycles, to machine vision systems inspecting glaze coverage, every step is optimized for consistency, safety, and speed. The machinery involved is custom designed, often proprietary, and requires teams of trained technicians to maintain. Clean-in-place systems are installed throughout the facility to sanitize pipes, mixers, glaze troughs, and conveyors between production runs. This minimizes downtime while ensuring compliance with food safety regulations. Every aspect, from microbial swab testing to allergen control and traceability, is monitored via centralized software platforms, which can track each batch of donuts from flour silo to store shelf. The story of every M&M starts with one essential component: chocolate. The heart of a standard M&M is a solid drop of milk chocolate, though other varieties, like peanut, almond, crispy, pretzel, or peanut butter, feature different cores. But regardless of the variety, the production begins in the chocolate refining department, where raw ingredients such as cocoa liquor, cocoa butter, sugar, and milk solids are blended to make a smooth, consistent chocolate base. The chocolate used in M&Ms is tailored for firmness and melt resistance, specifically engineered to maintain its structure during the coating process. Large stainless steel tanks are used to melt and hold the chocolate at controlled temperatures. Automated valves and mixers regulate temperature, viscosity, and flow characteristics. Chocolate destined for M&M production must be carefully refined to reduce particle size, usually to around 20 microns. This is done in multiple stages using equipment like ball mills, roller refiners, and conchers. These machines apply friction, pressure, and shear force to break down the solid particles until the chocolate achieves its desired mouthfeel. Once refined, the chocolate is pumped to depositors, automated nozzles that precisely dispense the liquid chocolate into molds or droplet-forming equipment. For the classic M&Ms, the chocolate is dropped onto a cool, rotating belt in small, round portions, forming button-shaped discs. These droplets are cooled rapidly using chilled air tunnels to harden them before further processing. The cooled chocolate centers are then collected and sent to the coating drums. These are large rotating pans, sometimes referred to as dragees pans or coating kettles, where the hard candy shell is gradually built around the chocolate core. This is the heart of the M&M production process and one of the most visually striking steps in the factory. The coating process is a slow and incremental buildup, achieved by spraying a fine mist of sugar syrup onto the tumbling chocolate centers, then drying and hardening that layer before repeating the cycle. Each coating drum can hold hundreds of thousands of chocolate centers at once. As the drum rotates, a fine spray of syrup, consisting mainly of sugar and water with optional corn syrup, is applied in short bursts. Warm air is then blown into the drum to dry the layer, allowing the sugar to crystallize into a thin, hard shell. This cycle is repeated dozens of times, each time adding a microscopically thin layer to build up the final shell thickness. Over time, this layering transforms the centers from soft chocolate buttons to perfectly round, hard-shelled candies. During this stage, technicians monitor coating uniformity, size consistency, and drying times using high-speed cameras and inline sensors. If the temperature or humidity in the coating room deviates too far from spec, it can ruin an entire batch, leading to shell cracking or poor adhesion. Once the desired shell thickness is achieved, the M&Ms are polished to give them their signature shine. This is done by adding polishing agents, such as carnauba wax or beeswax, to the coating drum in very small amounts. These natural food-grade waxes help create a glossy finish that not only enhances visual appeal, but also helps prevent sticking and moisture absorption during storage. The polishing phase takes less time than coating, but must be precisely timed to avoid overwaxing, which can result in a greasy or smeared appearance. The next step is color application, which may seem simple, but is, in fact, a carefully controlled phase. M&Ms come in a variety of colors, typically red, orange, yellow, green, blue, and brown. The color coding is applied using a sugar-based dye solution, sprayed in another round of layering inside rotating pans. Each batch is divided according to how many of each color are required. Food-grade colorants are mixed with water and a binding agent to ensure even adherence to the existing shell. After the colorant is applied, warm air is used to dry the layer, and another wax polish may be added to lock in the color and maintain shine. The factory uses precise batch tracking and automated scheduling software to ensure the correct number of each color is produced. For example, if red accounts for 20% of a standard bag's color distribution, the system ensures exactly that percentage is created during the run. This attention to detail keeps the consumer experience consistent across bags, boxes, and geographic regions. After color coding, the candies proceed to the printing station, where the iconic M is stamped on each piece. This is accomplished using high-speed, food-safe ink printers. The M&Ms are gently vibrated into a single layer on a moving conveyor belt that aligns them properly for stamping. The white edible ink is applied using a flexographic or offset stamping mechanism that imprints the M logo without damaging the candy surface. To ensure accuracy, machine vision systems monitor the printing in real time, checking for clarity, alignment, and completeness. Any candies that are misprinted or blank may be removed by pneumatic air jets and diverted for recycling or reprocessing. Now the M&Ms are ready for packaging. This phase of production involves a combination of robotics, weight-checking systems, and packaging machinery that operates at astonishing speeds. The candies are directed into vertical form-fill-seal machines or horizontal flow wrappers, depending on the packaging format. Multi-head weighers dispense precise quantities of M&Ms into each bag or pouch, ensuring weight compliance to legal standards. The packaging film is heat-sealed to form a tamper-evident, airtight barrier that preserves freshness and extends shelf life. For bulk formats, such as large tubs, party-sized bags, or vending packs, the process is slightly different but still highly automated. The machines are programmed to handle various product sizes, materials, and pack types without compromising accuracy. Barcodes, expiration dates, and lot numbers are printed onto each package to allow for traceability. Once packaged, the products are conveyed to case packing robots, which group them into cartons or boxes for shipping. These cases are then sealed, palletized by robotic arms, and shrink-wrapped for transport. Pallets are stored temporarily in climate-controlled warehouses before being loaded onto distribution trucks that carry them to retail centers, convenience stores, vending machine suppliers, and international shipping hubs. Throughout the entire process, food safety and quality control are paramount. The factory floor is governed by strict hygiene protocols. Employees are required to wear sanitary gear, and the equipment is sanitized regularly using automated clean-in-place systems. Random sampling is conducted at every critical control point, from chocolate refining to shell thickness to final packaging. Laboratory testing checks for microbial contamination, allergen presence, and chemical composition. Quality assurance teams also perform taste tests, structural integrity tests, and heat resistance trials to ensure the product meets Mars Inc.'s global standards. In the case of peanut or almond M&Ms, the process is similar but begins with nut preparation. Peanuts, for instance, are roasted in-house to develop their flavor and reduce microbial load. They are then cooled, sorted by size, and coated in a preliminary layer of chocolate before undergoing the same sugar shell layering process. Their irregular shape requires adjustments to coating speed and rotation patterns to ensure even coverage. The engineering behind M&M production is not only a marvel of food science, but also a study in high-speed manufacturing. Thousands of M&Ms can be produced every minute, yet each one must look and taste exactly the same. This requires the coordination of multiple disciplines: mechanical engineering, chemistry, automation, logistics, and sensory evaluation. The process begins not with whole potatoes, but with dehydrated potato flakes and potato starch. These form the base of the Pringles dough. The flakes are manufactured off-site through a separate drying process where peeled, cooked potatoes are mashed and then passed through drum dryers to remove water, creating thin, crisp sheets of dried potato. These are ground into fine granules and delivered to Pringles production facilities in bulk quantities, stored in climate-controlled silos to maintain moisture levels and prevent clumping. To this potato base, manufacturers add a precise blend of rice flour, corn flour, and wheat starch. This multi-starch formula gives Pringles their distinctive light, yet durable crunch, firmer than a classic chip, but less dense than a cracker. Each ingredient is selected for its functional properties. Rice flour contributes to lightness and reduces oil absorption. Corn flour provides structure and contributes to the crisp texture. Wheat starch acts as a binding agent and helps form the dough into a cohesive sheet. Inside the factory, these dry ingredients are metered into high-capacity industrial mixers. Water is added gradually, and the mixture is agitated until a cohesive dough forms. The consistency of the dough is critical. It must be pliable enough to be rolled and shaped, yet stiff enough to hold its form during frying. Too much water would cause the crisps to bubble and deform. Too little, and they would crack or crumble during processing. After mixing, the dough is conveyed onto a series of steel rollers in a sheeting machine. These rollers press the dough into a continuous, thin sheet, typically about 0.7 to 1 millimeter thick. The uniformity of this sheet is crucial, as even slight thickness variations can affect how the chips fry, blister, and brown. Advanced sensors mounted near the rollers continuously monitor sheet thickness, feeding data to the control system, which makes micro adjustments in real time. Next, the sheeted dough passes under a rotary die cutter. This is a cylindrical cutter with thousands of identically shaped molds engraved into its surface. As the sheet moves beneath it, the die cuts out dozens of curved oval crisps at a time, each one precisely measured to match Pringles' iconic dimensions, around 6.5 centimeters long and 5.5 centimeters wide, shaped with a unique double-curved profile known as a hyperbolic paraboloid. This mathematical shape isn't just aesthetic, it offers stackability, strength, and an audible crunch due to its uniform stress distribution. The dough scrap that remains between the cutouts is immediately separated and returned to the beginning of the process. Conveyor belts collect and transport the unused dough back to the mixer, where it is reincorporated into fresh dough. This closed-loop system minimizes waste and ensures efficiency in ingredient usage. Once cut, the raw crisps are gently lifted from the sheet using suction cups or air jets and placed onto a moving metal belt composed of dozens of concave molds. Each mold perfectly matches the chip's final saddle shape. This belt then moves the raw crisps into the fryer, an enormous stainless steel bath filled with hot vegetable oil, maintained at a consistent temperature of around 170 to 180 degrees. The crisps are submerged for approximately 11 seconds, long enough to remove moisture and induce a Maillard reaction, giving them their light golden brown hue and toasty flavor. Unlike traditional deep-fried potato slices that can curl, bend, or form bubbles, the Pringles molds maintain each crisp's structure during frying. Because the crisps are uniformly thin and precisely shaped, they fry evenly with no dark spots or oil saturation. Excess oil is quickly removed as the crisps exit the fryer and pass over a series of vibrating conveyors and air knives, high-pressure jets that blow away any surface oil or crumbs. At this point, the freshly fried crisps are hot, dry, and unseasoned. They move into the seasoning tunnel, a long, rotating drum equipped with sprinklers or spray nozzles. Here, flavor powders, ranging from classic original to sour cream and onion, cheddar cheese, or barbecue, are evenly applied as the crisps tumble and rotate. The flavor powders are formulated to stick to the crisp's surface via residual oil left from frying. In some varieties, additional ingredients such as powdered cheese or dehydrated vegetables are included in the seasoning blends. To prevent flavor loss and preserve freshness, the seasoned crisps are quickly cooled using forced air systems before entering the packaging phase. This cooling is critical. If the crisps are too warm, condensation can form inside the package, leading to soggy chips and microbial risk. Once cooled, they are conveyed to the stacking and canning line. This is where another defining feature of Pringles becomes prominent: their tubular canister. The stacking machine uses a system of synchronized mechanical arms, optical sensors, and robotic paddles to stack crisps one by one into perfectly aligned columns. This process is remarkably fast and precise. A sensor verifies each crisp's shape and orientation before it's inserted into the growing stack. Once a full stack reaches the correct height, typically around 80 to 100 crisps, depending on the packaging size, it is inserted vertically into a cardboard can that's been pre-formed and lined with a metallized film to prevent oil seepage and moisture intrusion. Each can is equipped with a plastic bottom, which is ultrasonically welded or heat sealed in place before filling. After the crisps are inserted, a foil lid is applied and hermetically sealed using induction heat or pressure bonding to ensure an airtight closure. A plastic snap-on cap is then placed on top, providing resealability for consumer convenience. The filled cans are then labeled and date-coded. Each can receives a printed batch number and expiration date to ensure traceability throughout the distribution chain. Vision inspection systems scan each can to ensure it is filled to the correct level, sealed properly, and free of any external defects like dents or mislabeling. Cans are grouped into multi-packs or cartons by robotic arms and placed on pallets for storage or shipment. Depending on demand and product line complexity, different varieties of Pringles may be produced in separate production runs on the same line, requiring quick and thorough cleanouts between batches to prevent flavor cross-contamination. From here, Pringles are shipped to distribution centers, retailers, and convenience stores across the globe. Thanks to the uniform shape and rigid packaging, they travel exceptionally well, with minimal breakage compared to traditional bagged chips. This durability, coupled with the brand's distinct identity, has made Pringles a staple in global snack markets. Sanitation and quality control are central throughout the process. Each stage of production, from dough mixing to final packaging, is monitored by automated control systems and human operators. Random samples are collected for lab analysis to check moisture levels, oil content, seasoning distribution, and texture. Microbial testing ensures no contamination occurs during handling. Metal detectors and X-ray machines inspect each can before shipping to catch any foreign objects that may have entered the line. Allergen controls are strictly enforced, particularly when switching between varieties like original and cheddar cheese. In addition to ensuring food safety, the factory design and equipment layout support continuous cleaning. Many machines feature clean-in-place systems that pump sanitizing fluids through the equipment without requiring disassembly. Air filtration systems and positive pressure rooms minimize the risk of dust and airborne contaminants affecting product quality. Beyond the manufacturing floor, the creation of new Pringles flavors and formats involves food scientists and R&D specialists who develop seasoning blends, test mouthfeel, and conduct sensory panels with trained tasters. Innovations like Pringles Wavy or Pringles Scorchin follow the same base process, with minor adjustments in dough formulation or seasoning protocols. Despite their high-tech origin, Pringles still deliver a simple satisfaction, a crisp, flavorful bite that feels familiar and fun. But behind that enjoyment is a complex dance of precision equipment, mathematical shaping, and carefully designed formulations. From powdered potatoes to perfectly stacked crisps, every Pringle is a product not just of flavor, but of industrial ingenuity. A testament to how food science can transform something as humble as a potato into a globally recognized snack. The core of every Sour Patch Kid is a soft, chewy matrix primarily composed of sugar, corn syrup, gelatin, and various fruit flavors. These ingredients must be blended in precise proportions to achieve the specific texture that Sour Patch Kids are known for. Not as firm as gummy bears, not as sticky as fruit snacks, but perfectly chewy with a fast melt in the mouth. The sugar and corn syrup form the bulk of the candy. Sugar provides structure, sweetness, and contributes to the candy's crystal clear translucence, while corn syrup prevents the sugar from recrystallizing and keeps the final product soft and elastic. These two are delivered to the factory in bulk. Sugar often in railcars or tanker trucks, and corn syrup in heated stainless steel tankers to maintain fluidity. In the batching area of the facility, massive stainless steel mixing kettles are used to combine sugar, corn syrup, and water. The mixture is heated to dissolve the sugar and initiate cooking. Industrial mixers stir the solution constantly, while steam-jacketed walls evenly raise the temperature to around 230 degrees to 250 degrees, depending on the desired consistency and final moisture content. At this stage, the mixture is highly viscous, resembling hot, liquid sugar syrup. Once the sugar solution is properly cooked, gelatin is added. Gelatin is the key protein that gives Sour Patch Kids their elastic chew. It's derived from collagen, typically from pork or beef, and arrives at the factory as a dry powder. It is hydrated in warm water in separate tanks and added to the sugar syrup only after the syrup has cooled to an appropriate temperature to avoid denaturing the gelatin. This step transforms the hot sugar mixture into a viscoelastic candy base. At this point, citric acid and tartaric acid are introduced. These two organic acids are what provide that first intense sour kick when you bite into a Sour Patch Kid. They are used at very specific levels. Too little, and the candy loses its iconic tang. Too much, and the texture or shelf stability may be affected. Food scientists spend years perfecting this balance. In addition to acidulants, artificial and natural fruit flavorings are also added, usually concentrated solutions of compounds that mimic cherry, lemon, lime, orange, blue raspberry, and other classic flavors. Color is next. Each flavor of Sour Patch Kid is dyed with specific food-grade colorants. These are either synthetic or naturally derived, like beet juice or turmeric extract, depending on the formulation and market regulations. These colorants are added to the mix during the blending phase in tightly controlled amounts to ensure vibrancy and uniformity across batches. Once the hot candy mixture is fully mixed, it is ready to be molded. Sour Patch Kids are molded using a starch mogul system, a technique used for generations in gummy candy manufacturing. The starch mogul line begins with large trays filled with cornstarch. These trays pass under a stamping head fitted with dozens of Sour Patch Kid-shaped molds. The stamps press into the starch, forming hundreds of identical candy-shaped impressions per tray. The hot, syrupy candy mass is poured into these impressions using heated depositors. The candy flows smoothly into each cavity, forming the familiar, tiny humanoid shape. These trays, now filled with thousands of candy molds, are stacked and moved into drying rooms, also known as curing chambers. Here, the candies rest for 24 to 48 hours in warm, dry conditions. The cornstarch helps wick away moisture from the candy, allowing it to firm up without collapsing or becoming sticky. During this curing period, the gelatin sets fully, giving each candy its final chewable texture. After curing, the trays are sent to a destarching station. Here, the starch is separated from the candies using rotating sifters and vibration tables. The excess starch is collected, filtered, and reused in future molding cycles. The Sour Patch Kids, now fully formed and firm, are tumbled through gentle conveyors to remove residual starch. Now comes the most distinctive part of the process, the sour sugar coating. This is what gives Sour Patch Kids their unique mouth-watering appeal. The coating consists of a blend of fine granulated sugar, citric acid, and tartaric acid. The finished candies are placed into large rotating pans or coating drums, similar in appearance to cement mixers, but designed specifically for food products. As the drums rotate, the candies tumble over one another, while a fine mist of water or sugar solution is sprayed lightly to help the sour powder adhere. Simultaneously, the sugar acid blend is sprinkled in. The result is a uniform, crystalline coating on every piece. Timing and rotation speed are key here. Too much coating and the candy becomes overwhelming and sticky. Too little and the signature tang is lost. Factory technicians carefully monitor coating weights and perform quality checks throughout the shift to ensure product consistency. After coating, the candies are passed through a drying tunnel or cooled in ambient air to set the coating. They are then conveyed to an inspection area where cameras, sensors, and sometimes human inspectors check for shape, color, and coating uniformity. Any malformed or off-spec candies are removed from the line. Now it's time to package the final product. Sour Patch Kids are typically packed into portioned pouches, multi-serve bags, or retail cartons. The packaging line begins with form-fill-seal machines, high-speed systems that unroll printed plastic film, form it into pouches, fill each pouch with a measured weight of candy, and then seal it shut using heat. These machines are calibrated to ensure each pack contains the right amount of product and is sealed airtight for freshness. The sealed pouches are then coded with date stamps, batch numbers, and sometimes QR codes for traceability. They are dropped into shipping cartons or display cases, depending on the destination. These cartons are weighed, barcoded, and stacked automatically onto pallets. From there, the pallets move to temperature-controlled warehouses, where they await shipment to stores, vending distributors, movie theaters, and supermarkets. Throughout the factory, food safety is the top priority. Every step, from ingredient receiving to packaging, is conducted under good manufacturing practices. Workers wear protective clothing, hairnets, and gloves. Equipment is cleaned between production runs. Acid-resistant stainless steel and food-grade plastics are used throughout the facility. Environmental controls manage humidity and air filtration to ensure cleanroom-level hygiene in production zones. Sour Patch Kids production also involves detailed analytical testing. Random samples are pulled from each batch and tested in quality control labs for pH, moisture content, acid levels, color uniformity, texture, and shelf life stability. Sensory panels evaluate flavor consistency and sour-sweet balance. If any parameter is off, adjustments are made in the next batch, or the lot is held for investigation. As candy demand has grown, the process has become even more efficient through automation and smart technology. Modern factories use real-time data monitoring systems to control temperatures, mixer speeds, and depositor rates. Predictive maintenance software ensures machinery stays operational. Ingredient inventory is tracked digitally, and computerized dosing systems eliminate human error in weighing acids or colorants. Sustainability has also become a key consideration. Factories producing Sour Patch Kids increasingly aim to reduce water use, lower energy consumption, and source gelatin from suppliers who practice ethical sourcing. Even the packaging films are being redesigned in some regions to be recyclable or biodegradable. When the candy finally reaches store shelves, it has already traveled a long journey, from raw gelatin and sugar to the smiling, sour-coated figures we all recognize. Each bite delivers not only flavor, but the culmination of chemistry, engineering, and candy artistry. The sour then sweet experience isn't just a slogan, it's a precisely engineered sensory journey that begins with a sharp, puckering acid hit and fades smoothly into fruity, mellow sweetness. The process begins with the core ingredients: sugar, corn syrup, water, flavorings, and colorants. These are the building blocks of Jolly Ranchers, but the way they are combined and treated in the factory determines the final product's success. Sugar and corn syrup are delivered in bulk to the manufacturing plant, sugar often in powder or granulated form, and corn syrup as a thick liquid shipped in insulated tanker trucks to keep it warm and flowable. In the batching room, large stainless steel kettles are used to combine sugar, corn syrup, and a small amount of purified water. The goal is to dissolve the sugar and initiate a high-heat cooking process that transforms these ingredients into a highly concentrated, clear candy base. This cooking step is key. Jolly Ranchers are a type of hard candy, which means the sugar mixture must be cooked to what's known in confectionery as the hard crack stage, around 300 degrees to 310 degrees. These cooking kettles are jacketed with steam coils or electric heating elements that allow precise temperature control. As the mixture heats, the water begins to evaporate and the syrup thickens significantly. This evaporation is critical. It's what ultimately leaves the candy with such a low moisture content that it becomes glassy and brittle once cooled. Industrial stirrers keep the mixture agitated to ensure even cooking and prevent hot spots or scorching. As the syrup approaches the target temperature, automated sensors closely monitor the heat and viscosity. If the temperature is even slightly off, the final texture of the candy could be compromised. Undercooked syrup results in a sticky or chewy texture, while overcooked syrup becomes too brittle or may develop a burnt flavor. Once the sugar syrup reaches the perfect consistency, it's time to add the key components that give Jolly Ranchers their personality: flavor and color. The candy base is divided into smaller batches, each destined to become a different flavor: cherry, watermelon, green apple, blue raspberry, grape, and others. Each batch is transferred to flavoring tanks or mixing troughs where concentrated food-grade flavorings and dyes are added. These flavor compounds are highly concentrated and added in very specific ratios. Natural and artificial flavorings are used depending on the formulation. For example, a cherry Jolly Rancher might include benzaldehyde for that sharp, almond-like cherry punch, while green apple flavor could rely on malic acid esters for its tart kick. The colorants are also carefully chosen to match the expected visual identity of the flavor. Red 40, yellow 5, blue 1, and other FDA-approved synthetic dyes are often used in varying combinations to produce the vivid hues. Mixing must be fast and efficient at this stage because the candy syrup is still extremely hot and starts cooling quickly. Mixing arms or ribbon blenders integrate the flavor and color without introducing air bubbles, which would compromise the candy's clarity and structure. At this point, the flavored and colored syrup begins to thicken rapidly and takes on the consistency of hot, pliable taffy. Timing is critical. If it sets too quickly, it becomes unworkable. The next step is forming. Unlike many other candies that are molded in starch trays, Jolly Ranchers are formed using a process known as rope forming and die stamping. The hot candy is transferred onto cooling tables or through temperature-controlled rollers where it is shaped into thick, cylindrical ropes. These ropes are slowly cooled as they pass through stainless steel rollers and conveyors. The goal is to bring the candy down to a workable temperature where it can be cut and stamped, but not yet hardened completely. Once the candy ropes are at the right consistency, they pass through a forming machine fitted with precision dies. These dies stamp and cut the candy into individual pieces, each with the familiar oblong pillow shape. The forming machine applies enough pressure to ensure a clean cut, but not so much that it distorts the candy's surface. This is a delicate operation, as the candy is beginning to crystallize and solidify rapidly. The cutters must be kept heated or treated with food-safe lubricants to prevent sticking and preserve the clean edges of the final product. After forming, the individual Jolly Ranchers move on to a cooling conveyor system. These long, slowly moving belts expose the candies to progressively cooler ambient air or cooled forced air, gradually lowering their internal temperature. This slow cooling is important to prevent cracking and to ensure the surface remains glossy. If cooled too quickly, internal stresses could form, making the candy brittle or causing it to become cloudy. Once fully cooled and solid, the candies head to the wrapping stage. Each Jolly Rancher is immediately wrapped in a specially designed waxed film or polypropylene-based wrapper that prevents sticking and maintains freshness. Wrapping machines operate at extremely high speeds, feeding candies into synchronized rollers that twist wrap or fold seal each piece. The wrappers are pre-printed with branding, flavor indicators, and batch codes for traceability. The wrapped candies are then collected into large bins or counted into packaging units. Depending on the product line, Jolly Ranchers might be bagged into share-size pouches, fun-size treat bags, or bulk cartons. Form-fill-seal packaging equipment handles this part, weighing exact quantities of candies, dropping them into bags formed from a continuous roll of printed film, then sealing the bags with heat to to make them tamper-evident and shelf-stable. As the candies are packaged, quality control plays a key role throughout the process. Random samples are taken and tested for color accuracy, size uniformity, hardness, and moisture content. Hardness tests may involve durometers or similar equipment that measures resistance to pressure, ensuring the candy has the right glass-like firmness. Flavor panels may also evaluate taste intensity, checking for flavor balance and clarity. If a batch is found to be off-spec, it may be rejected, reworked, or diverted to secondary markets. Behind all this precision lies rigorous food safety protocols. Workers wear gloves, hairnets, and lab coats in production areas. Machines are sanitized regularly, and allergen controls are in place even though Jolly Ranchers typically contain no nuts, dairy, or gluten. Hazard analysis and critical control point systems are used to identify and mitigate risks at each step of the process. From the moment the sugar is received to the point where a wrapped candy is sealed in a bag, every movement is monitored and recorded for traceability. Additionally, modern Jolly Rancher production facilities are incorporating automation and smart factory technologies. Recipe management systems ensure precise ingredient dosing, and digital controls allow managers to adjust batch temperatures and cooking times from central dashboards. Optical sensors inspect wrappers for misprints. Even the temperature and humidity of production rooms are computer controlled to maintain consistent output regardless of the season or climate outside. Sustainability is also being addressed in newer production lines. Energy-efficient kettles and heat recovery systems help reduce fuel use. Water used in equipment cleaning or steam generation is recycled where possible. Wrapping materials are being developed with recyclability in mind, and many facilities are exploring biodegradable or compostable film options. The finished Jolly Ranchers, now bagged and boxed, are stacked onto pallets and moved into climate-controlled warehouses for distribution. These candies are remarkably stable, with long shelf lives due to their low moisture content and protective wrapping. This makes them ideal for global shipping. From there, they head to supermarkets, convenience stores, vending machines, and movie theaters all around the world, ready to deliver that unmistakable burst of sour cherry, green apple, or blue raspberry flavor. It all begins with the selection and preparation of the raw ingredients. At the core of every Haribo gummy candy is a combination of sugar, glucose syrup, gelatin, citric acid, fruit flavoring, and food coloring. These ingredients must be carefully sourced and managed to ensure the consistent taste, texture, and appearance that consumers expect. Sugar and glucose syrup form the base of the gummy. These are typically delivered to the Haribo factory in large quantities, sugar in bulk containers or silos, and glucose syrup in insulated tankers to maintain fluidity. In the production facility, the sugar and glucose syrup are fed into large stainless steel kettles equipped with steam jackets and stirring paddles. The mixture is gently heated and stirred to fully dissolve the sugar crystals, creating a thick, sweet solution. This sugary base is the fundamental building block for all Haribo products. Once the sugar solution reaches the appropriate concentration and temperature, gelatin is introduced. Gelatin is a key functional ingredient in Haribo gummies, providing their characteristic chewiness and structure. It is typically derived from pork or beef collagen and arrives at the factory in dehydrated granule or sheet form. Before it can be added to the sugar mixture, the gelatin is first hydrated in warm water in separate mixing tanks. Once fully dissolved, the gelatin is combined with the hot sugar syrup under controlled conditions. The resulting mixture is carefully heated to a precise temperature, usually around 150 to 160 degrees, ensuring full integration of the gelatin without degrading its gelling ability. During this step, any acids such as citric acid or malic acid are also added. These acids are responsible for the pleasant tang that balances the sweetness of the candy and enhances the fruit flavors. Next, the flavorings and colors are introduced. Haribo uses a range of natural and artificial fruit flavors to create its signature gummy taste profiles. Each flavor, lemon, orange, raspberry, pineapple, and apple, among others, is blended in concentrated liquid form and carefully metered into separate batches of the hot candy mix. Food-grade colorants are added alongside the flavorings, giving each candy its bright, transparent hue. The combination of flavor and color must be exact to meet Haribo's internal standards, and flavor technicians often perform sensory evaluations during production. With the flavored and colored syrup fully prepared, it is ready for the molding process. Haribo gummies are formed using a traditional confectionery technique known as starch molding, or the starch mogul system. This process begins with large trays filled with cornstarch. A molding board presses bear-shaped cavities into the surface of the starch, creating hundreds of individual molds per tray. The hot, viscous candy mixture is poured into these molds using automated depositors equipped with multiple nozzles. Each nozzle dispenses the exact volume of syrup needed to fill a single bare cavity, ensuring uniform size and weight across thousands of pieces. The trays are then stacked and transferred to a curing room, a warm, dry environment where the candies are allowed to set for 24 to 48 hours. During this curing period, the gelatin network solidifies, giving each gummy its final elastic texture. The starch not only supports the shape, but also absorbs moisture from the surface of the candy, helping to achieve the perfect skin. Once the gummies are fully cured, the trays are sent to a destarching machine. This piece of equipment gently tumbles the trays, separating the candy pieces from the cornstarch. Vibrating screens and air jets remove any excess starch, which is collected, filtered, and reused in the molding process. The newly formed gummies, now free of starch and fully set, are inspected and prepared for the next stage. Now comes the coating process, which adds shine and improves handling. Haribo gummies are typically coated with a thin layer of food-grade wax, such as carnauba wax or beeswax, and vegetable oil. This coating is applied in rotating drums or tumblers, where large quantities of gummies are gently mixed while a light mist of the wax solution is sprayed over them. The result is a glossy surface that prevents the candies from sticking together and enhances their visual appeal. The wax also serves as a moisture barrier, helping to preserve the candy's freshness during storage and transport. After coating, the gummies pass through a final inspection phase. This includes both visual inspections by trained staff and automated optical systems that check for shape uniformity, color consistency, and size accuracy. Any defective or malformed candies are removed from the line and discarded or recycled, depending on the facility's protocols. Next, the candies move on to the packaging line. Haribo uses a range of packaging formats, including peg bags, share-size pouches, single-serve packs, and multi-flavor assortments. The packaging process begins with high-speed form-fill-seal machines. Printed plastic film is unrolled and shaped into pouches, which are then filled with a precise weight of gummies. The bags are sealed using heated jaws that bond the plastic layers together, creating an airtight, tamper-evident package. The filled bags are then printed with production information such as batch number, expiration date, and sometimes promotional codes or QR codes for consumer engagement. They are packed into cartons, stacked onto pallets, and moved to the warehouse where they await distribution. Throughout this final stage, quality control teams monitor the sealing integrity, fill weights, and print accuracy to ensure compliance with product specifications. Behind the scenes, every Haribo production facility operates under strict food safety and quality assurance protocols. These include adherence to good manufacturing practices, hazard analysis and critical control points, and ISO quality standards. Production areas are cleaned regularly, equipment is sanitized, and every batch is traceable from raw ingredient to finished product. Samples are pulled at every stage and tested in on-site laboratories for pH, moisture content, texture, and microbial safety. Modern Haribo factories also make use of advanced automation and data analytics. Ingredient dosing is controlled by programmable logic controllers to reduce human error. Sensors monitor cooking temperatures, gelatin concentration, depositor output, and humidity levels in real time. Production managers can access digital dashboards to track performance metrics and respond quickly to any deviations. These innovations not only improve efficiency, but also support the consistency that Haribo is known for. As a global brand, Haribo also customizes its recipes and flavors for different regions. For example, gummies produced in Europe may use natural colorings derived from fruit and vegetable concentrates, while US products may include certified synthetic dyes. Flavors may also vary to suit local preferences, such as blackcurrant in the UK, mango in Asia, or sour varieties in North America. Despite these differences, the core manufacturing process remains largely the same across all Haribo facilities. Sustainability is another growing focus in Haribo's operations. The company has been investing in renewable energy, water conservation, and waste reduction across its factories. Ingredient sourcing increasingly considers environmental impact and animal welfare, particularly in the sourcing of gelatin. Packaging materials are being re-evaluated to include recyclable films and reduce plastic usage. When a bag of Haribo Gold Bears finally lands on store shelves, it represents a highly coordinated blend of traditional candy-making techniques and modern industrial precision. Each chewy bear is the product of strict formulation, controlled cooking, precise molding, and sophisticated quality checks. From sugar kettle to glossy, colorful treat, the journey of a Haribo gummy is a testament to the art and science of confectionery manufacturing. While the candies may be playful and whimsical, the process behind them is anything but casual. It requires the coordination of food engineers, quality control experts, maintenance technicians, flavor developers, and packaging specialists, all working together to ensure that every handful of Haribo delivers the same beloved taste and texture, whether it's made in Germany, the United States, or anywhere else Haribo operates. This level of consistency and care is what has allowed the brand to thrive for over a century, making Haribo gummies a global favorite that continues to delight generation after generation. Reese's Peanut Butter Cups begin with the bulk delivery of raw peanuts to the factory's intake silos, where they are gravity-fed into the initial sorting system. These peanuts are inspected mechanically, using a combination of vibrating sieves and optical sorters to remove any debris, underdeveloped kernels, or foreign materials. Once sorted, the peanuts move via enclosed conveyors to massive gas-fired rotary roasters. These roasters tumble the peanuts at temperatures ranging from 160 to 180 degrees Celsius for up to 30 minutes, depending on the batch specifications. Uniform roasting is critical, as it directly impacts the flavor profile of the peanut butter core. Immediately after roasting, the peanuts are dropped into rapid cooling bins to halt the cooking process. Once cooled, they're transported to a dry deskinning machine, where rubber-lined rollers strip the outer skins, which are then removed via airflow separators. The cleaned roasted peanuts are directed into hoppers that feed them into industrial grinders. The first stage produces a coarse paste, while the second stage refines this paste into a smooth, semi-solid mass with just enough texture to give Reese's its signature, slightly grainy peanut butter. At this stage, the peanut paste is blended with dextrose, salt, and a small quantity of vegetable oil stabilizers in jacketed mixing tanks. These tanks are equipped with high-torque agitators that ensure uniform mixing and prevent separation. The peanut butter is then pumped into storage tanks held at a steady 40 degrees Celsius to maintain pourability, with recirculation loops preventing oil separation. While the peanut butter is being prepared, the chocolate coating is simultaneously processed in a different section of the plant. Solid chocolate blocks arrive in insulated pallets and are broken down into manageable chunks by automated crushers. These chunks are melted in conical tempering kettles, where the chocolate is cycled through precise temperature phases. Heating to 45 degrees Celsius to dissolve fat crystals, cooling to 27 degrees Celsius to encourage type 5 crystal formation, and then reheating slightly to 30 to 31 degrees Celsius to prepare for molding. This tempered chocolate is fed through stainless steel piping with heated jackets into the deposition zone. The chocolate is deposited into paper-lined plastic molds using servo-controlled nozzles. The molds are pre-fitted with pleated paper cups, automatically dispensed and placed by robotic arms. The bottom layer of chocolate is dispensed in a circular motion to form a consistent base. The molds are gently vibrated on a plate to spread the chocolate evenly and eliminate air bubbles. Once the bottom shell is semi-set, the peanut butter is deposited in the center using another set of volumetric piston fillers. Each dollop is carefully controlled to ensure it stays centered and does not bleed into the side walls, which would prevent the top chocolate layer from sealing properly. The peanut butter is slightly cooler than the chocolate to preserve its form as it's deposited. The top chocolate layer is applied almost immediately after the peanut butter centers are deposited. Another set of nozzles applies tempered chocolate to fully enrobe the filling, again followed by brief vibration to ensure complete coverage and smooth surface finish. This layered structure of chocolate, peanut butter, and chocolate is the signature of every Reese's cup, and the volumes are calibrated down to the milliliter. Next, the filled molds enter a tiered cooling tunnel. This tunnel is divided into climate zones, with each zone dropping in temperature by small increments, from 20 degrees Celsius down to around 8 degrees Celsius, over the course of 15 to 18 minutes. This gradual cooling prevents thermal shock, which could cause cracking or separation between the chocolate and filling. Each zone is equipped with air circulation fans, refrigeration coils, and humidity control systems to ensure perfect crystallization of the chocolate. After the cooling process is complete, the now fully formed Reese's cups are ejected from their molds using a pneumatic plunger system that pushes from beneath the mold cavities. The cups remain in their paper liners and are transferred to conveyance lanes for wrapping. At this point, the cups are still exposed and vulnerable to environmental conditions, so the transfer occurs within a controlled, filtered air enclosure to prevent contamination. The wrapping process uses horizontal flow wrappers. Each Reese's cup is aligned via guide rails and funneled into individual wrapping lanes. Printed foil is unwound from rolls and cut to size by rotary knives. The cup is pushed onto the foil by a mechanical arm, and the foil is folded and sealed around the candy using heat-sealing jaws that close in fractions of a second. The wrapped cups are then printed with batch codes and expiration dates using inkjet or thermal printers. For king-size or multi-cup packages, the single wrapped cups are automatically grouped and loaded into larger overwrap film using a secondary wrapping machine. These packages are then loaded into display cartons by robotic pick-and-place arms that orient each unit for retail presentation. These cartons are glued or tab sealed, then labeled with product identifiers, shipping information, and QR codes for traceability. Before packaging is finalized, random samples are pulled from each production batch and sent to quality assurance labs. Here, technicians weigh each cup, examine chocolate gloss and thickness under calibrated lighting, and use penetrometers to test the firmness of the peanut butter. They also cut cross-sections of the cups to visually inspect layering uniformity and check for air gaps or structural flaws. Once cleared, finished cartons are palletized using robotic stacking systems that build stable load units based on truck optimization software. Each pallet is stretch wrapped and labeled with RFID tags that track its origin, contents, and destination. These pallets are loaded onto climate-controlled trucks that maintain the cargo area between 10 degrees Celsius and 22 degrees Celsius, preventing chocolate bloom or melting during transport. Even after the cups leave the factory, Hershey maintains control over their handling through advanced logistics software. This platform integrates sales forecasts, retailer data, and shipping conditions to prioritize inventory rotation and ensure that product closest to expiration is delivered first. Warehouses use automated pick systems and real-time barcode scanning to manage stock. In addition to the standard production line, seasonal Reese's cups, like pumpkin or heart shapes, are produced using interchangeable mold plates. These specialty shapes require adjustments in chocolate and filling deposition to accommodate varied volume and geometry. The same precision is applied to these runs, though the visual inspection is even more rigorous due to complex shapes. Flavor innovation is handled through a separate R&D pipeline. Variants like white chocolate or dark chocolate cups require their own tempering parameters and material handling systems to prevent cross-contamination. These are produced in small trial batches on modular production lines until formulations are approved for full-scale production. From a sustainability perspective, Hershey continuously works to reduce energy and material waste. Chocolate tempering kettles use thermal recirculation systems to recover heat energy, while the roasting exhaust is captured and scrubbed for reuse in preheating systems. All peanut skins, chocolate trimmings, and off-spec cups are collected and either reprocessed or converted into animal feed and energy through biodigesters. This entire system, roasting, grinding, tempering, depositing, cooling, wrapping, inspecting and shipping, operates in a tightly synchronized loop, monitored by real-time factory control software. Supervisors can access dashboards showing throughput, downtime, temperature profiles, and ingredient usage. Alerts notify operators of any deviations from specification, and corrective actions are logged for traceability. Every Reese's cup, whether it's a classic 2-pack or a seasonal novelty, is the result of layered processes fine-tuned to deliver the exact same flavor and texture every time. From the precise ratio of peanut to salt, to the sheen on the chocolate, to the shape of the paper liner, all of it is the product of exacting industrial craftsmanship. Mars chocolate bar production starts with the arrival of key ingredients at the facility: raw cocoa mass, cocoa butter, sugar, skimmed milk powder, lactose, glucose syrup, and proteins used in the nougat layer. All ingredients are subject to strict quality control before entering the production line. Cocoa mass and butter are delivered in solid block form, stored in climate-controlled zones, and tested for fat content, aroma, and particle size. Sugar arrives in bulk and is transferred pneumatically into silos. Milk powders are delivered in sealed containers, sampled for moisture and purity, then funneled to automated dosing stations. The chocolate phase begins with tempering and mixing. Cocoa mass and cocoa butter are first melted in stainless steel, jacketed tanks at precise temperature ranges, typically between 45 degrees Celsius to 50 degrees Celsius. This molten chocolate mixture is sent into high-capacity blenders, where sugar, milk powders, and lactose are added. The mixing process creates a coarse paste which then undergoes refining. Refining is done using 5-roll refiners, massive machines where the chocolate paste passes through a series of increasingly narrow steel rollers. These rollers compress the paste down to a fine particle size between 20 to 30 microns. This size range ensures that the final chocolate feels silky and not gritty. Sensors monitor the output continuously for particle size and adjust roller pressure accordingly. The refined paste is moved into conching machines, where it's heated and agitated for several hours. Conching removes volatile acids and moisture while developing flavor and viscosity. Emulsifiers like soy lecithin are added during this phase to control flow behavior. The conched chocolate is then pumped into holding tanks kept at 30 to 32 degrees Celsius, ready for use in barcoding and mold filling. In parallel, the nougat layer is being produced in a different section of the factory. Mars's nougat starts by mixing sugar, glucose syrup, and water in large cookers. This mixture is heated to form a syrup, which is transferred to industrial aerators. Here, whipped protein, often derived from egg whites or hydrolyzed soy protein, is added. The high-speed aerators incorporate air into the mix, giving nougat its light, chewy texture. Once whipped, the nougat is enriched with milk powder, fats, and flavoring components to build creaminess and mouthfeel. The warm, aerated nougat is extruded onto a continuously moving conveyor belt as a wide, flat slab. As it travels down the line, it is cooled by overhead airflow units to partially set its structure. Once firm enough, the nougat sheet is trimmed to a uniform width using high-speed rotary blades and moves to the caramel deposition stage. Mars caramel is produced using continuous vacuum cookers. Sugar, glucose syrup, and milk ingredients are heated under vacuum to lower the boiling point, preserving soft texture and rich dairy flavor. Once the caramel reaches the desired consistency, it is deposited as a thin, even layer over the traveling nougat base. This layered slab now resembles the cross-section of a Mars bar before chocolate coating. Cooling tunnels set the caramel onto the nougat layer using a staged drop in temperature from ambient to around 10 to 12 degrees Celsius. Once the slab is fully set, it moves to ultrasonic cutters. These high-frequency blades cut the slab into bar-length segments with minimal compression, maintaining clean edges and uniform size. Each bar now contains a core of structured nougat and a top layer of soft caramel, and is ready for chocolate coating. The next stop is the enrobing line. Each bar is placed onto a perforated conveyor belt and passes through a chocolate curtain, molten tempered chocolate falling in a continuous sheet. A bottoming roller ensures the underside is coated first. Air knives blow off excess chocolate and shape the final bar profile. Edge trimming guides ensure the sides are evenly coated without pooling. The entire chocolate coating process is conducted at controlled temperatures, usually around 30 degrees Celsius, to maintain chocolate viscosity and gloss. Once coated, the bars enter a long, refrigerated cooling tunnel. This tunnel gradually lowers the temperature over multiple zones, ensuring that the chocolate sets smoothly without cracks or bloom. Cooling takes roughly 12 to 15 minutes. Humidity is strictly controlled throughout to prevent condensation on the bars. Upon exiting the cooling tunnel, the bars are transferred to the wrapping station. Each bar is aligned into feeding lanes and enters a horizontal flow wrapper. Printed packaging film is unwound and formed around each bar. The wrapper is sealed using heat and pressure at the ends and along the back. Prior to sealing, the package interior may be flushed with nitrogen gas to remove oxygen and extend shelf life. Barcodes, batch codes, and expiry dates are printed in real time using high-speed inkjet printers. Cameras verify print legibility and seal integrity, and any faulty packages are ejected from the line. Accepted bars are automatically grouped into cartons, 12, 24, or 36 count configurations, depending on destination and retail requirements. Cartons are sealed with glue or interlocking flaps and labeled with destination codes. Palletizing robots stack cartons onto wooden or plastic pallets using algorithms that maximize load stability and cube efficiency. Once stacked, the pallets are stretch wrapped with plastic film and labeled with RFID tags containing tracking and batch data. These pallets are transported via forklifts or automated guided vehicles to temperature-controlled storage areas. Inventory management systems track product age and availability in real time. Orders are picked and dispatched using a just-in-time system integrated with retailer demand signals and distribution schedules. In addition to core Mars bars, the same line can be configured to produce variations such as fun size, twin pack, or regional editions. Changeovers involve switching cutting equipment, recalibrating depositor heads, and swapping packaging materials. This flexibility allows Mars to meet seasonal demand spikes or promotional formats without building entirely new production lines. Throughout the process, dozens of sensors, cameras, and feedback systems maintain quality. Chocolate viscosity is tracked with inline viscometers. Weight checks are performed on each bar using precision scales, and metal detectors ensure product safety. Quality control technicians also pull random samples hourly to inspect cross-sections, flavor, and mouthfeel. Sensory testing panels taste test bars daily to ensure consistency. Waste is minimized through rework systems. Off-spec nougat and caramel are reprocessed when possible, and chocolate trimmings are collected and remelted for future batches. Scraps unsuitable for reuse are converted to animal feed or processed through waste-to-energy systems. Sustainability initiatives have also taken hold. Mars uses responsibly sourced cocoa certified by third-party organizations and invests in water reduction systems and energy recovery technology in its factories. Packaging material is being reformulated for recyclability and reduced plastic usage. Each Mars bar, though it appears simple, is the product of a deeply engineered process, combining food chemistry, automated manufacturing, and strict quality assurance to ensure uniformity on a scale of millions of units per day. From raw cocoa mass to wrapped bar, the journey is a marvel of food industry precision. Snickers bars begin their life in a highly coordinated manufacturing facility where precision equipment, food science, and industrial engineering merge to produce one of the world's most popular candy bars. The process starts at the very foundation, the peanuts. Whole, raw peanuts arrive at the factory in food-grade bulk containers or via pneumatic tankers. These nuts are funneled into intake hoppers equipped with vibrating screens and magnets to remove stones, shells, or metal fragments. From there, they're transferred to silos with humidity and temperature controls, where they await roasting. The roasting process is crucial in developing the Snickers bar's signature crunch and roasted aroma. The peanuts are moved from silos into rotary drum roasters, which tumble them continuously at temperatures between 160 to 180 degrees Celsius. The roasting cycle is tightly timed, usually around 20 to 25 minutes, and computer systems monitor kernel temperature, moisture release, and color development using near-infrared sensors. Once roasting is complete, the peanuts are transferred to a cooling conveyor where chilled, filtered air rapidly reduces the kernel temperature, halting the cooking process and preserving the ideal crunch. After cooling, the peanuts are split into two processing streams. A portion is designated for whole peanut inclusion. These go through size grading systems and optical sorters that scan for broken or discolored nuts. Defective peanuts are automatically removed with precise puffs of air. The selected whole peanuts are sent to temporary storage hoppers until they are needed at the assembly stage. The other stream is milled into granulated peanut fragments. The peanuts pass through precision grinders that can be adjusted to produce different textures, from coarse granules to fine peanut meal. These different textures are essential as the coarse fragments are used in the caramel mixture for crunch, while the finer ones enhance the nutty flavor in the nougat. While the peanuts are being processed, the nougat, a critical layer in every Snickers bar, is produced in an adjacent line. The nougat base is made by mixing glucose syrup, sugar, powdered milk, and a whipped protein sauce, typically egg whites or hydrolyzed soy protein, isolate. These ingredients are heated in a batch cooker where sugar and glucose syrup dissolve and are cooked to a specific temperature to ensure the right consistency. The hot syrup is pumped into an aeration chamber where it's rapidly whipped to incorporate micro bubbles of air, turning the dense syrup into a light, chewy base. To this base, ground peanut meal and sometimes cocoa powder are added, depending on the variation of Snickers being produced. The aerated nougat mixture is deposited onto a moving steel conveyor belt in a uniform slab, usually about 10 to 15 millimeters thick. The slab is leveled with motorized spreaders to ensure consistency in thickness, and then it enters a cooling tunnel. The tunnel gradually brings down the temperature of the nougat slab using fans and chilled air, solidifying the structure just enough for it to carry additional layers without collapsing. The next step is caramel preparation. caramel for Snickers is not a generic mixture. It's custom designed for the brand's chewy, stretchy mouthfeel. It begins with a combination of glucose syrup, sugar, milk solids, and butter, cooked under vacuum to reduce the boiling point and develop flavor while maintaining softness. This caramel is cooked in large, continuous cookers that can process hundreds of liters per hour. The caramel is cooled slightly and mixed with coarse ground peanuts, creating the crunchy, rich upper layer of the bar. This hot caramel peanut mixture is deposited directly onto the cooled nougat slab. The deposition system includes a manifold that spreads the mixture evenly across the slab, forming a second layer. This dual-layered slab continues down the production line into another cooling tunnel, where the caramel firms up without hardening completely, remaining flexible for cutting. Once sufficiently cooled, the dual-layer slab is transported to the guillotine cutter. Using ultrasonic or hot wire blades, the slab is cut into bar-width strips and then into individual bar lengths, usually 50 to 60 grams each. These bars are then conveyed into the enrobing line, where they receive their final layer, chocolate. The chocolate coating used on Snickers bars is made in-house, using a proprietary blend of cocoa mass, cocoa butter, sugar, and milk powders. These ingredients are refined and conched in large machines that heat, mix, and aerate the chocolate to develop flavor and reduce particle size. The finished chocolate is held in jacketed tanks at a precisely controlled temperature of 30 to 32 degrees Celsius, ready for tempering. Tempering involves carefully controlling the crystallization of cocoa butter to ensure that the final chocolate has the right snap, gloss, and shelf stability. The tempered chocolate is pumped into enrobing machines, long tunnels, where a curtain of liquid chocolate coats the bars as they move along a mesh conveyor. A bottoming wheel applies chocolate to the underside of each bar, ensuring full coverage. Excess chocolate is removed using air knives, and the bars are passed under vibrating plates to level the coating. The coated bars are conveyed into a cooling tunnel approximately 20 to 30 meters long. The temperature in the tunnel drops from room temperature to about 8 to 10 degrees Celsius in graduated steps. This controlled cooling sets the chocolate without causing bloom or shrinkage. By the time the bars emerge, they are fully formed and ready for packaging. Each Snickers bar is picked up by robotic arms and placed into horizontal flow wrapping machines. Printed packaging film is formed around the bar, sealed at both ends and along the back using heat sealing jaws. The sealed bars are printed with a batch number, expiry date, and traceability code. Optical scanners inspect each package for proper seal integrity, print clarity, and alignment. The wrapped bars are grouped into cartons using high-speed collation systems. Depending on the SKU, bars may be packed into boxes of 12, 24, or 48 units. The cartons are sealed, labeled with logistics and traceability data, and palletized by robotic stacking systems. Pallets are shrink-wrapped and moved to staging areas for shipment. Throughout this entire process, quality assurance plays a vital role. Inline sensors and cameras continuously monitor chocolate viscosity, nougat density, caramel flow rate, peanut distribution, and packaging integrity. Manual samples are taken hourly and cut open for cross-sectional inspection. Taste tests are conducted daily by trained sensory teams who evaluate aroma, flavor, mouthfeel, and visual quality. Products that fail any stage of inspection are diverted, documented, and analyzed to prevent recurrence. Snickers factories are designed with food safety and hygiene as top priorities. Staff wear full PPE, including hairnets, gloves, and smocks. Entry to production areas requires hand washing, sanitization, and often passing through air showers or floor sanitizers. All surfaces are made of food-grade stainless steel, and machinery is built with clean-in-place systems that allow automated washing and sanitization between batches. Environmental sustainability is another integral part of Snickers manufacturing. Mars, the parent company, implements energy-efficient roasting systems that recover heat, water reclamation systems that treat and reuse rinse water, and LED lighting to cut emissions. Chocolate and nougat trimmings are collected and either reused in new batches or converted into animal feed, while packaging material waste is recycled or reused wherever possible. From the first roasted peanut to the moment the wrapper is sealed, the making of a Snickers bar involves over a dozen steps, hundreds of parameters, and thousands of quality checks. Every component, from the protein foam in the nougat to the precise shear profile of the caramel, the fat crystal structure of the chocolate, and the crunch of the peanuts, has been engineered and tested to deliver a consistent, craveable bite. This integration of traditional confectionery with high-efficiency industrial production is what enables Snickers to be produced in the millions each day, while maintaining the same rich, multi-layered flavor and texture that has made it a global staple for decades. The production of Hershey's chocolate, from raw cocoa beans to the smooth, creamy bars found in stores across the globe, is a finely tuned industrial process that combines traditional chocolate-making techniques with large-scale factory automation. The journey begins with the sourcing of raw ingredients and extends through roasting, grinding, conching, tempering, molding, and packaging, all carefully orchestrated to deliver Hershey's signature taste and texture in every bar. The process starts at the very beginning of the supply chain, the harvesting and sourcing of cocoa beans. Hershey sources its beans primarily from West Africa, including countries like Côte d'Ivoire and Ghana, where cocoa trees grow in tropical climates. Once harvested, the beans are fermented under banana leaves or in wooden boxes for several days. This crucial step develops the deep chocolate flavor. After fermentation, the beans are sun-dried, sorted for quality, and bagged for export. Upon arrival in the US, Hershey's manufacturing facility inspects every shipment, checking for size, moisture content, and the absence of mold or pests. The beans are then conveyed into the cleaning and sorting machinery, where they pass through vibrating sieves, pneumatic suction tubes, and magnetic separators. This removes twigs, stones, dust, and any metallic particles. The cleaned beans are stored in large silos, kept dry and temperature controlled to preserve freshness. From here, they enter the roasting stage, which is one of the most important parts of flavor development. In the roasting stage, cocoa beans are fed into large rotating drums that heat them to between 120 and 150 degrees Celsius for about 30 minutes. The temperature and duration are carefully adjusted depending on the bean variety and flavor profile desired. During roasting, volatile acids are reduced and deep chocolate notes are intensified. The process also loosens the shells from the nibs, the edible inner part of the bean. As the roasted beans exit the drums, they move into the winnowing machine. The winnowing process uses high-speed fans and friction rollers to crack the roasted beans and separate the lighter shells from the heavier nibs. The result is a large volume of cocoa nibs, the pure form of chocolate, which are then transferred to grinding mills. These heavy-duty industrial grinders reduce the nibs into a thick, brown liquid called chocolate liquor or cocoa mass. Although the term liquor might sound alcoholic, it refers here to the liquefied state of cocoa solids suspended in cocoa butter due to the heat generated during grinding. Next, Hershey separates the chocolate liquor into cocoa butter and cocoa solids using hydraulic presses. The cocoa butter is a pale yellow fat that contributes to the creamy mouthfeel of chocolate, while the cocoa solids are rich in flavor. Hershey stores both components separately in stainless steel vats. For milk chocolate, which is the company's primary product, the recipe also calls for sugar, milk, lecithin, and flavoring ingredients like vanillin. One of Hershey's defining characteristics is its use of fresh milk, a distinguishing factor that sets it apart from European chocolatiers who often use powdered milk. In fact, Hershey operates its own dairy processing facilities in Pennsylvania. The milk is condensed and cooked with sugar to form a sweet, caramelized base that's blended with chocolate liquor and cocoa butter. This mixture is the beginning of Hershey's signature milk chocolate formula. This blend is then dried into chocolate crumb, a key intermediary unique to Hershey's process. The crumb is a dry, flaky mixture of milk solids, sugar, and chocolate liquor. It's stored in silos and later rehydrated with cocoa butter and emulsifiers during the refining stage. Creating crumb allows for a longer shelf life of the milk solids and helps develop the brand's distinctive, slightly tangy, malty flavor due to controlled milk fat breakdown during the crumb formation. Next comes refining, where the crumb and cocoa butter are combined and passed through a series of steel rollers. These rollers gradually reduce the particle size of sugar and cocoa to less than 30 microns. This fine reduction is critical for achieving the smooth mouthfeel of chocolate. If particles are too large, the texture becomes gritty. Too small, and it can feel pasty or dull on the tongue. The mixture exits this stage as a smooth, semi-fluid paste, ready for the next critical transformation, conching. In the conching process, the chocolate paste is agitated in large conche machines, steel troughs with granite or metal rollers that knead, heat, and aerate the chocolate continuously for up to 72 hours. This stage allows for further evaporation of unwanted volatile acids, the smoothing out of flavor edges, and the development of chocolate's rich, complex notes. The friction in conching also ensures the even distribution of cocoa butter, giving Hershey's chocolate its desirable melt-in-your-mouth quality. After conching, the chocolate is tempered. Tempering is the controlled crystallization of cocoa butter to ensure the chocolate sets with a glossy finish and satisfying snap. Hershey employs large-scale automated tempering units that carefully heat and cool the chocolate through a series of steps, bringing it down from around 45 degrees Celsius to 31 to 32 degrees Celsius for milk chocolate. This aligns the fat molecules into a stable crystalline structure, which gives the final bar its appealing texture and helps it resist bloom, where fat rises to the surface in white streaks. Once tempered, the liquid chocolate is piped into molds. The molding line consists of high-speed stations where molds are filled, vibrated to eliminate air bubbles, and chilled using cooled air or glycol-jacketed trays. For Hershey's iconic bars, molds are embossed with the brand's lettering and evenly segmented for snapping. The filled molds travel on a conveyor through a cooling tunnel that solidifies the chocolate completely within 8 to 12 minutes. Once cooled and hardened, the chocolate bars are demolded using a combination of vacuum systems and gentle mechanical actuators that pop them out without breakage. They move immediately into the packaging area, where a series of synchronized operations wrap, seal, label, and code each bar. Hershey's uses flow wrapping machinery that envelopes each bar in a foil and paper sleeve or film, depending on the product. The wrappers are printed with batch codes, best before dates, and product tracking identifiers. Every bar then undergoes quality control, which includes weight checks, X-ray scanning for foreign particles, and visual inspection by cameras that detect surface defects. Samples from each batch are taken to an on-site lab where texture, flavor, and microbiological safety are tested. If any irregularity is found, entire lots can be isolated thanks to the full traceability built into the production system. The packaged bars are then packed into cartons and stacked on pallets by robotic arms. The pallets are shrink-wrapped, barcoded, and sent to the distribution center. Hershey maintains temperature-controlled warehouses to ensure product stability, especially during summer months or shipments to warmer climates. Pallets are loaded into refrigerated or insulated trucks for distribution to stores across the country and abroad. What makes Hershey's chocolate truly unique isn't just the equipment or the ingredients, but the balance between automation and sensory control. While the machinery ensures consistency at massive volumes, sensory panels and chocolate experts continuously evaluate flavor, aroma, and texture to ensure every bar delivers the recognizable Hershey's profile. Even at the scale of hundreds of thousands of bars per day, this commitment to flavor accuracy and quality control is what maintains Hershey's reputation in the competitive world of confectionery. From cocoa bean to final bar, the industrial process behind Hershey's chocolate is a fascinating example of how tradition and technology merge. Every step, from roasting and grinding to conching and tempering, is carefully measured, controlled, and optimized. The result is a product that is not only nostalgic for many, but is also the outcome of over a century of engineering refinement and food science innovation. Cadbury's chocolate, with its unmistakably smooth texture and rich, creamy flavor, is one of the most beloved chocolate brands in the world. Its manufacturing process, while steeped in over a century of heritage, is executed today through a blend of tradition, advanced automation, and rigorous food science. At Cadbury's major production sites, such as the iconic Bournville factory in Birmingham, UK, every bar begins with careful ingredient sourcing and continues through precise steps involving milling, refining, conching, tempering, molding, and packaging. Across each stage, quality control, consistency, and signature taste are paramount. The first step in Cadbury's chocolate-making journey is the selection of raw ingredients. Cadbury's signature milk chocolate is made from a combination of full cream milk, sugar, cocoa butter, cocoa mass, and emulsifiers such as lecithin. Cadbury is known for using a relatively high percentage of milk solids compared to other mass-market chocolates, which contributes to its uniquely creamy flavor. For the UK and several international markets, Cadbury still uses fresh liquid milk rather than powdered or condensed forms. The milk is delivered daily to factories from nearby dairy farms, stored in chilled stainless steel silos, and constantly stirred to prevent separation. Meanwhile, cocoa beans, the fundamental ingredient in any chocolate, arrive at Cadbury's factories from West Africa, particularly Ghana, which provides a consistent, high-quality bean that is fermented and sun-dried prior to export. Upon arrival, these beans undergo detailed quality inspections before entering the factory system. They are cleaned thoroughly to remove foreign matter, dust, sticks, stones, or metal particles through a series of sieves, aspiration towers, and magnetic separators. Once clean, the beans are roasted. The roasting stage is one of the most vital steps for developing the chocolate's flavor. Cadbury uses hot air roasting techniques in rotating drum ovens or continuous flow systems, depending on the production volume. The temperature typically ranges from 120 to 150 degrees Celsius, and the roasting time can vary from 20 to 40 minutes. During roasting, the complex chemical reactions that form the Maillard compounds intensify the chocolate aroma and flavor, while also drying the beans to the ideal moisture level for further processing. After roasting, the beans are cooled and passed through winnowers, machines that crack them open and use air currents to separate the outer shells from the inner nibs. These cocoa nibs are rich in fat and flavor and form the base of both the cocoa mass and cocoa butter used in Cadbury products. The nibs are ground in heavy-duty mills to produce cocoa liquor, a thick, chocolatey paste made from pure nibs. Though liquid due to the heat generated during grinding, this liquor is made up of both cocoa solids and cocoa butter. At this point, the chocolate-making process diverges depending on the final product. For Cadbury dairy milk and similar products, a crucial step involves combining the cocoa liquor with sugar and milk. Cadbury's defining feature is its use of fresh milk, which undergoes its own separate treatment. The milk is condensed with sugar in heated vacuum evaporators, producing a thick, rich liquid. This mixture is then blended with cocoa liquor and cocoa butter to create a homogeneous chocolate base. In traditional British-style chocolate making, as Cadbury does, this mixture is then dried into what is known as milk chocolate crumb. This dry crumb is unique to Cadbury and imparts a signature caramelized, malty undertone that distinguishes it from chocolates made with powdered milk or Swiss-style processing. The crumb is produced by drying the combined milk, sugar, and chocolate mixture in large drum dryers or vacuum drying systems, resulting in a sandy, dry granule that is easy to store and rehydrate in later stages. The crumb is stored in large silos until needed. When it's time to produce finished chocolate, it is remixed with additional cocoa butter, sometimes more cocoa liquor depending on the product, and emulsifiers like lecithin. This mixture is then passed through refining rollers, a series of 5 steel cylinders that reduce the particle size of the sugar and cocoa solids. The aim is to reach a uniform particle size of around 20 to 30 microns. This gives the chocolate a smooth texture without feeling gritty on the tongue. Particle size is verified using laser diffraction particle analysis systems to ensure consistency across every batch. Once refined, the chocolate enters the conching stage, named after the shell-like shape of early conching machines. This process involves mixing, shearing, and aerating the chocolate over several hours, anywhere from 4 to 24 hours, depending on the product. Conching removes volatile acids, unwanted moisture, and any rough flavor edges. Cadbury uses both traditional longitudinal conches and modern rotary conches, depending on the scale and specific chocolate formulation. During this time, the texture becomes silkier and the flavor deepens and rounds out. Following conching, the chocolate is transferred to the tempering line, one of the most delicate and technically controlled stages in chocolate manufacturing. Tempering involves carefully cooling and reheating the chocolate to encourage the formation of stable cocoa butter crystals, which give chocolate its shiny appearance and clean snap. Improper tempering can result in chocolate bloom, a whitish, dull coating caused by fat separation. Cadbury's tempering machines operate in a closed-loop system, cycling chocolate through a precisely controlled thermal curve. Advanced digital sensors monitor viscosity, temperature, and flow characteristics to ensure optimal temper structure. Once tempered, the chocolate is ready for molding. Cadbury's high-speed molding lines pour the liquid chocolate into molds made of polycarbonate or food-grade stainless steel, depending on the product. The molds pass over vibration plates to eliminate air bubbles and ensure even distribution. The filled molds then travel through a cooling tunnel that gradually reduces their temperature to solidify the chocolate without causing stress fractures. This ensures a uniform, glossy appearance and the correct snap when broken. Demolding is performed using vacuum lifters or gentle mechanical knockers, depending on the mold shape. For filled products like Cadbury cream eggs or caramel bars, the process includes an additional step. Shell molds are created by partially filling and spinning molds to create a cavity, which is then filled with the flavored fondant or caramel using precision depositor heads. These centers are allowed to partially set before a chocolate-based layer is applied, and the molds are fully sealed, then cooled and demolded just like solid bars. Once the chocolates are demolded, they move directly to the packaging lines. Here, automated machinery wraps individual bars in foil and branded sleeves or flow wraps them in film. The packaging materials are printed with batch codes, expiry dates, and traceability data. Optical scanners and X-ray systems perform real-time quality checks, looking for surface imperfections, air gaps, or foreign matter. Any product not meeting the strict standards is ejected from the line automatically. The wrapped bars are then grouped into cartons or multi-packs, which are robotically packed into shipping cases. These cases are barcoded, palletized by robotic arms, and shrink-wrapped for shipping. pallets are stored in temperature-controlled distribution centers until they are shipped out to retailers. The entire inventory system is managed using enterprise-grade software that tracks each chocolate bar from production to warehouse to store shelf. What distinguishes Cadbury's industrial chocolate production from others isn't just its recipe, but its integration of craftsmanship and automation. Despite being a global brand, producing millions of bars per week, Cadbury maintains tight control over flavor, texture, and appearance through every stage, from the exact ratio of milk solids to the particle size in refining and the thermal curves of tempering. Every sensor, every conveyor, and every batch record plays a part in delivering a final product that's as familiar as it is meticulously engineered. Even sustainability is built into the process. Cadbury's factories are gradually moving toward carbon neutrality, with newer systems recovering heat from roasting for use in conching, and solar panels offsetting daytime energy use. Additionally, cocoa is increasingly sourced through the Cocoa Life program, which promotes fair trade, farm productivity, and community development in West Africa. In the end, every Cadbury Dairy Milk bar is a result of over a century of refinement, rooted in British chocolate-making tradition, but carried out in some of the most sophisticated food production environments in the world. From fresh milk and raw cocoa to the purple-wrapped bar, every step reflects a balance of nostalgia and precision, heritage and innovation. Mars chocolate bars, instantly recognizable by their dark chocolate coating, nougat core, and caramel layer, are manufactured through one of the most highly refined industrial processes in the global confectionery world. While the experience of biting into a Mars bar feels simple and indulgent, the behind-the-scenes production is anything but. It requires precision control of temperatures, flow rates, ingredient ratios, and mechanical handling, executed across multiple synchronized systems in high-speed, high-volume manufacturing plants. The entire process, from raw ingredient reception to molded bars in wrapped form, is designed for repeatability, safety, and sensory consistency, ensuring every Mars bar tastes identical to the last, whether it's made in the UK, the US, or elsewhere. It all begins with sourcing the core components: cocoa, sugar, milk, glucose syrup, and fats. Mars procures its cocoa through long-term supply contracts with farms across West Africa, where cocoa beans are fermented and dried on site before being shipped to processing facilities. Sugar is sourced from sugar beets or cane, depending on the regional plant. The milk component often comes in the form of milk powder or condensed milk, chosen for stability and easier integration into industrial formulations. Mars also uses specialty fats, vegetable oils, and cocoa butter blends for different parts of the bar to achieve specific textures and melting properties. Each of these ingredients is subjected to stringent quality control upon arrival. Cocoa powder is tested for fat content, microbial load, and flavor integrity. Milk powder is checked for protein and moisture levels. Sugars are screened for crystal size and cleanliness. Once cleared, they are transferred to bulk storage systems that feed directly into the production lines through enclosed, pressurized delivery tubes to minimize contamination. The first component to be produced on the line is the nougat base, which forms the soft but chewy core of a Mars bar. Nougat for Mars bars isn't the traditional egg white variety seen in artisanal confectionery, but a carefully engineered formula based on a whipped blend of sugar, glucose syrup, hydrolyzed soy protein, and milk powder. The dry and liquid ingredients are first mixed in large batch tanks equipped with high shear mixers. The mixture is heated to approximately 120 degrees Celsius to dissolve all solids and activate syrup structure, then cooled rapidly as it enters the aeration system. Aeration is critical. The hot syrup is whipped with nitrogen gas, chosen over air or CO2 because it's inert and maintains longer shelf stability. This whipping happens in high-capacity continuous mixers equipped with rotor-stator assemblies that shear and expand the mass into a light, foamy structure. The density is controlled down to the gram per cubic centimeter using inline flow meters and laser sensors. The freshly aerated nougat is extruded onto a cooling belt made of food-grade stainless steel or polyethylene-coated fabric. The belt runs beneath a cooling tunnel where chilled air brings the nougat's temperature down to a manageable level for further layering. At this stage, it appears as an endless beige ribbon, roughly the width and height of a Mars bar. Next comes the caramel layer, which is produced in parallel and deposited directly onto the top surface of the nougat ribbon. Caramel in Mars bars is made from a cooked mixture of glucose syrup, sugar, dairy solids, and fats, brought to a high boil under vacuum to reach the right viscosity and prevent crystallization. Caramel cookers, jacketed stainless steel kettles fitted with vacuum systems, ensure that the water content is carefully reduced without burning the sugars or degrading the milk proteins. Once cooked, the caramel is pumped into a spread depositor, a mechanism that lays down a smooth, even layer of caramel over the moving nougat sheet. The temperature of the caramel during application is closely monitored, usually around 40 to 45 degrees Celsius, to maintain spreadability without melting the nougat underneath. As the composite sheet of nougat and caramel moves along the line, it enters a laminar cooling tunnel, where chilled air slowly brings both layers down to cutting temperature. This ensures that the final bar will maintain its shape during slicing. After exiting the cooling tunnel, the layered slab is conveyed to a guillotine cutter, an automated, high-speed mechanical blade that slices the continuous sheet into individual bar-sized pieces. The cutter is synchronized with the speed of the conveyor, allowing it to produce thousands of consistent cuts per hour without crushing or dragging the layers. Optical sensors track the integrity and alignment of each cut, automatically rejecting any malformed pieces before they move to the next phase. The sliced centers are now ready for enrobing in chocolate. Each nougat caramel piece is placed onto the in-feed conveyor of a high-speed chocolate enrober. This machine pumps liquid chocolate, produced from a blend of cocoa liquor, cocoa butter, sugar, milk powder, and emulsifiers, over the bar in a curtain-like flow. The bottoms are coated first by passing over a shallow chocolate bath. Then the rest is coated from the top and sides via falling curtains of tempered chocolate. The chocolate used in Mars bars is carefully tempered beforehand. Tempering is the process of heating, cooling, and reheating chocolate to create a uniform fat crystal structure, giving the coating its shine, firmness, and resistance to bloom. Mars uses fully automated tempering units that precisely control chocolate temperature to within fractions of a degree, cycling through heating coils and chilled plates in sequence before delivery to the enrober. As each piece exits the enrober, it passes over a vibration plate that shakes off excess chocolate and ensures even coverage. Some lines use air knives, streams of compressed air directed at specific angles, to remove chocolate buildup from the sides or base of the bar. The freshly coated bars then enter a cooling tunnel that runs for 15 to 20 meters, gradually reducing their temperature in controlled stages to prevent cracking or moisture condensation. These tunnels use chilled, dehumidified air at around 8 to 12 degrees Celsius. Once the chocolate has fully set, the bars proceed to the wrapping line. Here, high-speed flow wrapping machines encase each bar in metallized polypropylene film, heat sealing both ends and the back. Wrapping machines include inline printers that apply the best before date, batch number, and factory code directly onto the film. Optical scanners check each wrapper for print clarity, alignment, and seal integrity. Any bar with misaligned film or poor sealing is ejected from the line by pneumatic arms into a separate rework bin. Wrapped bars are counted and grouped into cartons, which are then sealed, labeled, and moved to robotic palletizing systems. Robots arrange cartons in predefined patterns onto pallets based on flavor, size, and shipping destination. Each pallet is barcoded and logged into Mars' ERP system for real-time traceability. Pallets are stored in climate-controlled warehouses maintained at 18 to 20 degrees Celsius and under 50% relative humidity to preserve the chocolate's shelf life and prevent bloom or fat migration. The entire production line is monitored via SCADA systems, software platforms that oversee machine parameters, product flow, and quality metrics in real time. Operators at control stations can view temperature logs, flow rates, equipment performance, and reject rates. If a sensor detects even a slight deviation, like a variation in caramel viscosity or enrobing temperature, alerts are issued and adjustments are made immediately to avoid wasting product or compromising quality. The manufacturing journey of Doritos begins long before the chips ever hit the fryer or the seasoning drums. It starts in the cornfields. Doritos use a specific variety of whole kernel yellow corn selected for its starch content, moisture levels, and particle uniformity after grinding. The corn is harvested at peak maturity and tested for aflatoxins, foreign material, and protein content before it's even accepted at the plant. Only corn that passes this first round of quality standards is brought in for processing. At the factory, truckloads of bulk corn arrive daily and are funneled into underground receiving pits that use gravity to guide the kernels onto conveyor belts. These conveyors feed the kernels into the first stage of preparation, the cleaning and sorting system. In this system, the corn passes through an array of vibrating sieves, rotating drum sifters, and powerful pneumatic air classifiers. Large debris like cobs, sticks, or stones are removed first. Then, finer contaminants like dust and small broken kernels are extracted using aspirators that draw away lightweight particles. Magnetized rollers also scan the corn flow to remove any traces of ferrous metal, ensuring total cleanliness before cooking. Once cleaned, the corn moves into the nixtamalization phase, a crucial and traditional process that transforms the flavor, texture, and nutritional properties of the corn. Nixtamalization involves cooking the whole kernels in a large stainless steel vat of hot water mixed with food-grade calcium hydroxide, also known as slaked lime. The corn is cooked at around 85 to 90 degrees Celsius for approximately 20 to 40 minutes, depending on the batch size and corn variety. This lime water solution serves several purposes. It breaks down the outer pericarp of the kernel, making it easier to grind and digest. It also increases the bioavailability of niacin, softens the internal structure of the corn, and imparts the distinctive flavor profile that Doritos are known for. After cooking, the corn is not immediately processed but left to soak, usually for 8 to 12 hours in the same solution. This extended soaking allows the lime to fully penetrate the kernel and continues the softening and flavor-enhancing process. After the soaking phase, the corn is drained and rinsed thoroughly in large industrial washers that spray it with jets of clean water while gently tumbling the kernels. The goal is to remove the loosened pericarp, excess lime, and any residual cooking liquid. What remains is called nixtamal, a soft, pliable corn mass that still holds the shape of whole kernels, but has a meaty, hydrated texture. The nixtamal is now ready to be ground into masa, the dough-like base of every Dorito chip. The grinding is performed using industrial stone mills, rotating horizontal stones made of volcanic rock or synthetic composites, precisely aligned to maintain a consistent grind size. The nixtamal is fed between the stones, and the pressure shears the softened corn into a dense, cohesive paste. This paste is the masa, and its texture is critical. It needs to be soft enough to press, but dry enough to hold shape without sticking. Operators continuously monitor the temperature of the mesa during grinding. Too much friction can overheat the dough, which affects the final chip texture. Ideal mesa temperature coming off the stones is around 45 to 55 degrees Celsius. Viscosity is checked using inline sensors that measure flow resistance, and if adjustments are needed, small amounts of water or returned dry mesa are mixed back in using an automated feedback loop. Now, it's time to form the masa into flat sheets. The ground mesa is transported via auger screws into a sheeting machine, which extrudes the dough between two polished stainless steel rollers. These rollers are adjustable to control sheet thickness down to the millimeter, usually targeting between 1.2 and 1.8 mm, depending on the final chip specification. The mesa sheets are laid directly onto a continuously moving conveyor belt that carries them to the cutting station. The cutting system is a rotary die cutter, a high-speed drum outfitted with rows of equidistant triangular blades, each perfectly matched to the iconic Doritos shape. As the mesa sheet moves beneath the drum, the rotating blades stamp out thousands of identical triangle chips per minute. Each cut is sharp and precise, with just enough spacing to leave minimal waste dough between cuts. The trimmings, the thin slivers of masa between triangles, are not discarded. They are automatically lifted via vacuum collection and returned to the start of the sheeting process. These scraps are reincorporated into the fresh dough, ensuring efficient use of material and maintaining consistency. The cut triangle chips now move on a flat conveyor to a brief baking phase, which we'll explore in detail in the next section. This preliminary baking is vital to reduce moisture and stabilize the chip before it enters the high heat frying zone. But before any oil is introduced or seasonings are applied, this early stage, cleaning, nixtamalization, grinding, sheeting, and cutting, is where the foundation of Doritos' crunch, shape, and flavor truly begins. Once the precisely cut mesa triangles are formed and conveyed forward, they reach one of the most critical transitions in the Doritos factory, the pre-baking zone. Though often overlooked, this short but essential phase serves as a structural stabilizer that prepares each chip for frying without deforming, bubbling uncontrollably, or becoming overly saturated with oil. This stage controls the internal moisture content and builds the texture foundation that will result in the signature crunch. The masa triangles, still soft and slightly tacky from the sheeting process, move onto a continuous metal mesh conveyor belt that leads directly into an industrial tunnel oven. This pre-bake oven is not designed to fully cook or brown the chip. Instead, its primary goal is to reduce the moisture level from roughly 50% down to about 25 to 30%. This ensures the surface of the chip becomes firm enough to hold its shape when exposed to hot oil, but not so dry that it resists expansion. The oven itself is typically divided into multiple thermal zones. The first zone begins around 160 degrees Celsius, gradually increasing to about 260 degrees Celsius by the final section. Heated air is circulated by high-velocity blowers, creating a turbulent flow across the top and bottom of the chips to ensure uniform dehydration. The baking conveyor is made of stainless steel mesh that allows hot air to penetrate from below, guaranteeing that no side of the chip is undercooked. Sensors monitor humidity at various checkpoints, and real-time data is fed into the oven's PLC system to dynamically adjust airspeed and temperature depending on fluctuations in mesa density, ambient humidity, or line speed. As the chips exit the oven, they emerge firmer, drier, and more resilient, yet still pale in color and lacking the blistered surface texture that defines a finished Dorito. That transformation happens in the next stage, the continuous fryer system. Here, the par-baked chips fall gently off the oven belt and descend onto the infeed section of a massive open-surface fryer. The fryer itself is a high-capacity stainless steel vessel filled with continuously filtered cooking oil. Most Doritos production lines use either corn oil, sunflower oil, or a proprietary blend of vegetable oils chosen for their high smoke points and neutral flavor profiles. The oil is maintained at a stable frying temperature, of approximately 180 degrees Celsius, with variations of only +2 GC allowed during operation. Chips are submerged in the oil for about 35 to 55 seconds, depending on their exact moisture level and thickness. The chips ride through the fryer on a submersion conveyor, essentially a mesh belt with downward pressure bars that keep the chips fully immersed while preventing stacking or overlap. This is crucial because the frying process is not just about dehydration, it's about vaporization. As the residual water inside each chip turns to steam, it forces itself outward, puffing the chip slightly and creating those micro blisters and bubbly textures on the surface. This internal steam pressure is carefully managed. Too little and the chip stays flat and hard. Too much and it balloons into a hollow pocket. Above the fryer, exhaust hoods pull away steam and vaporized oil particles, filtering them through a heat recovery system that can reuse waste heat to pre-warm incoming oil. This system conserves energy and helps maintain a cleaner frying environment. The oil itself is constantly recirculated through centrifugal filters and fine mesh screens to remove crumbs, starch residues, or burnt particles. Fresh oil is added in controlled volumes throughout the day to maintain chemical balance and replenish lost volume. Once fried to the optimal light, golden color, the chips are lifted from the oil by an outfeed conveyor and immediately pass through a vertical de-oiling section. Here, powerful centrifugal blowers aimed at precise angles blast away excess surface oil. This keeps the chips crispy, prevents pooling in the packaging stage, and ensures that the seasoning will stick without creating grease buildup. The chips then pass through an ambient cooling tunnel to bring them quickly down to room temperature. Cooling is not merely for worker safety, it stabilizes the fat within the chip and prevents condensation when entering the seasoning drums. Now comes one of the most defining stages of the entire process: seasoning application. Each Dorito must carry the bold, vibrant flavor profile it's known for, whether that's nacho cheese, Cool Ranch, spicy sweet chili, or any of the dozens of global variants. The seasoning powder itself is a proprietary blend of flavorings, including real cheese powders, spices, salt, sugar, yeast extract, and encapsulated flavor oils that deliver controlled release bursts of taste. The chips are conveyed into a rotating seasoning drum, an inclined, slowly turning cylinder lined with food-grade stainless steel. As the chips tumble over one another, a dry powder dosing system mounted above the drum applies the seasoning using precision augers and dispersing nozzles. These nozzles can spray a uniform mist of oil if needed before the seasoning hits, which enhances adhesion for certain formulations. The rotation speed of the drum, the flow rate of the powder, and the incline of the system are all adjustable and carefully tuned. Too slow, and the powder won't distribute evenly. Too fast, and the chips may break, or the powder may collect unevenly on some sides. Optical sensors track the color and surface reflectivity of the chips as they exit the drum. If the reflectivity is too high, that could indicate under-seasoning. If it drops below a preset threshold, over-seasoning may be occurring. This live data is fed back into the controller, which tweaks the feed auger speed or pauses the oil spray accordingly. The seasoning drum is one of the most customized parts of the Doritos line. Different flavors use different particle sizes, densities, and oil volumes, which means the drum design and spray system must adapt depending on the product. Some drums include vibrating baffles or spiral lifts that increase tumbling action for extra thick chips or extra coarse seasoning. Once seasoned, the chips are directed into the weighing and bagging system, but before that, they undergo an automated inspection phase. High-speed vision cameras scan every chip for size, shape, and color. Broken chips, overly curled pieces, or visibly under-seasoned chips are removed via air-jet rejectors. These rejected chips are collected and sent either for regrinding or biomass energy use. Only chips that pass inspection enter the multi-head weighers, machines equipped with a dozen or more radial weighing hoppers. These hoppers constantly drop chips into a central collection bucket when the combined weight equals the target for each bag, typically between 28g and 198g, depending on package size. Once a precise combination is reached, the chips are dropped into a vertical form-fill-seal bagging machine. Here, continuous rolls of metallized polypropylene film are formed into tubes, sealed along the sides, and crimped at the bottom. The weighed chips are dropped into the formed bag tube just before the top is sealed and cut. Each bag is nitrogen flushed to displace oxygen, extending the product's shelf life and preserving crunch. Then, the bags are labeled, batch coded, and pass through a final metal detector before being boxed for palletization. After the freshly seasoned Doritos chips are individually weighed, bagged, sealed, and inspected, the production line moves into the critical post-packaging and logistics phase, where efficiency and traceability become as important as taste and texture. Though the chips are now fully formed and flavor complete, the operation is far from over. In fact, from a manufacturing systems perspective, the next stages, palletization, storage, shipping, and quality verification, are just as sophisticated and optimized as any in the earlier production line. The newly filled Doritos bags exit the form-fill-seal machines onto a series of conveyor belts designed to collect, orient, and organize them by SKU, bag size, and flavor variant. These conveyor lines merge into case packing stations, which use robotic arms equipped with vacuum suction grippers or gentle mechanical paddles to lift and place the chip bags into cardboard cartons. These boxes are pre-folded, glued, and printed with relevant product information, including product code, flavor, best before date, factory location, and a scannable QR or barcode that links to all production details. Each carton is inspected for weight and shape before it moves to the next phase. Even slight deviations in shape, caused by mispacked bags or an uneven number of chips, can disrupt downstream palletizing operations, so edge integrity and sealing quality are monitored automatically using high-resolution 3D scanning systems. Any carton that fails to meet dimensional tolerance is rejected from the main flow and rerouted for manual inspection or reboxing. Once cleared, the filled cartons are transferred to automated palletizing stations. In most modern Doritos factories, this process is entirely robotic. A multi-axis robotic arm lifts groups of cartons and stacks them onto wooden or composite pallets according to a predefined stacking pattern optimized for shipping efficiency and stability. These patterns are determined by a logistics algorithm that accounts for box dimensions, weight distribution, and the pallet's ultimate destination, whether that's a domestic warehouse or a long-haul overseas container. After each pallet is completed, a robotic stretch wrapper encircles it with several layers of clear plastic film to stabilize the load. A printed pallet ID label is affixed, containing detailed information about its contents, including product types, quantities, batch numbers, and destination. These labels are scanned into the warehouse management system, linking each pallet to the larger production database in real time. From here, pallets are routed into the warehouse zone. Doritos production facilities feature climate-controlled warehouses designed to maintain product quality throughout the storage period before distribution. These zones are not refrigerated, as Doritos are shelf-stable, but they are meticulously managed to avoid conditions that could lead to staleness or packaging deformation. Temperatures are generally held between 18-22 degrees Celsius, and humidity is controlled below 50% to prevent foil bags from absorbing moisture or warping. Inventory in the warehouse is managed by automated storage and retrieval systems. Tall racking structures are navigated by robotic cranes that pick and place pallets based on real-time demand, stock rotation policies, and shipping schedules. Each pallet's position in the warehouse is logged down to the specific shelf and column level, making retrieval highly efficient. The warehouse management system is integrated with the factory's enterprise resource planning software, ensuring that production and distribution are fully synchronized. While in storage, every pallet of Doritos is subject to randomized quality control sampling. A team of trained technicians removes sample bags from various pallets across shifts and production lines and sends them to a separate sensory evaluation lab within the facility. Here, samples undergo a series of tests: mechanical compression for bag integrity, gas analysis for nitrogen content, and oxygen intrusion, seasoning density checks, and most importantly, taste and crunch testing. Crunch is measured using a texture analyzer, a machine that applies controlled force to the chip and records resistance, fracture point, and acoustic feedback. The results are compared to golden standard reference chips to determine if the texture profile remains within acceptable limits. Seasoning adhesion and intensity are tested via flavor profile mapping, and every element from saltiness to umami to residual aftertaste is scored and compared against target values. If a trend of inconsistency is detected, an investigation is initiated, often leading to a review of upstream production parameters like fry temperature variability, seasoning drum throughput, or even ingredient batch variations. This closed-loop system helps prevent long-term quality drift and enables real-time course correction. Beyond the factory, the logistics infrastructure that gets Doritos from warehouse to retail shelves is another marvel of scale and precision. The factory works in tandem with PepsiCo's broader distribution network, which includes regional distribution centers, cross-dock terminals, and last-mile delivery nodes. Based on retail demand forecasts drawn from sales data, seasonal trends, and real-time POS metrics, shipment volumes are adjusted dynamically. This avoids overproduction and waste while ensuring retailers remain stocked. Each shipment of Doritos is accompanied by a digital bill of materials, which includes all traceability data from ingredient sourcing to packaging and palletization. This document allows not only for internal tracking, but also rapid action in the event of any product recall or customer complaint. If an issue is raised about a particular bag, say under-seasoning in a certain region, operators can trace the issue back to a specific lot, machine, shift, and even the original corn batch used in production. Globally, the manufacturing process for Doritos is also adapted based on regional consumer preferences and regulatory standards. While the foundational steps remain consistent: nixtamalization, sheeting, cutting, frying, and seasoning, the recipes and specifications can vary significantly. For example, in the US, cheese-based seasonings often use cheddar powder and lactic acid for tang, while in the UK or India, formulations may include less salt or alternative flavor enhancers to meet local guidelines or taste expectations. In markets like Japan or South Korea, where flavor sophistication and novelty are highly valued, factories produce limited edition Doritos featuring ingredients like wasabi, squid ink, or yuzu citrus. These variations often require changes in seasoning particle size, oil stability, or packaging material, and as such, the production lines must remain flexible. To facilitate this, Doritos factories use modular flavor dosing systems and quick changeover machines that allow seamless transitions between variants with minimal downtime. In addition to this flexibility, Doritos production lines are increasingly being outfitted with smart factory technologies. These include IoT sensors, predictive maintenance platforms, and AI-driven scheduling software. For instance, a vibration sensor might detect a subtle change in the seasoning drum's motor function that suggests a bearing is beginning to fail. Rather than waiting for a breakdown, the system automatically schedules maintenance during a planned production lull, avoiding unplanned downtime. Energy efficiency is also a growing focus. Waste heat from the fryers is often recovered through heat exchangers and used to preheat water for the nixtamalization tanks or warm the air in the seasoning room. Air filtration systems recycle hot air from the fryer exhaust into the building's HVAC to reduce natural gas usage. These sustainability practices help reduce both costs and environmental impact. Waste reduction is another area of innovation. Trimmings from mesa sheeting, broken chips, and seasoning dust are no longer treated as loss. Instead, they're collected, analyzed, and often reused in animal feed production, compost systems, or converted into biofuel at third-party processing facilities. Factory waste targets are set annually, and each production shift is scored on both yield efficiency and environmental impact. Ultimately, the journey of a Dorito from corn kernel to crunchy triangle is one of constant refinement. At every stage, whether it's dough hydration, fryer calibration, seasoning density, or robotic case packing, the process is governed by a matrix of mechanical precision and human sensory experience. The chips may seem simple to the average consumer, but behind every bag lies a production system that blends food science, industrial engineering, supply chain logistics, and consumer psychology into one unmistakable result: bold flavor, addictive crunch, and global brand consistency. It all starts with the Consumer Insight Team, which continuously analyzes sales data, social media trends, cultural food movements, and even fine dining innovation to identify gaps or opportunities in the market. A spike in interest around birria tacos, for example, might inspire a spicy beef consomme Doritos concept. Once a viable trend is spotted, food scientists and flavor chemists work alongside marketing strategists to develop flavor direction briefs, detailed documents that outline the intended taste profile, emotional positioning, and target audience. In PepsiCo's Flavor Innovation Centers, teams begin with flavor mapping. This involves breaking down target flavors into their basic aromatic and taste components. For a concept like Flamin' Hot Dill Pickle, the scientists would analyze heat components, acidity, herbal notes, and salt balance. Using GCMS, flavor chemists extract and replicate aromatic profiles to ensure they match real-life foods as closely as possible. Next, benchtop seasoning blends are created in small batches using food-grade flavor powders, encapsulated oils, anti-caking agents, and natural extracts. These are applied to test chips using miniature tumblers that mimic the behavior of full-scale seasoning drums. Each test batch is evaluated by sensory panels, trained tasters who assess flavor intensity, balance, aftertaste, aroma, and how the flavor interacts with the chip's natural corn and oil base. Their feedback is mapped against a flavor wheel to identify gaps or off notes that require reformulation. Multiple iterations are often needed. Some spices may clump, certain acids might degrade in heat, and some flavor oils could lose their punch after just a few days in packaging. Stabilizers and carriers are used to protect volatile components, and microencapsulation techniques ensure that heat-sensitive ingredients only release during mastication, not while sitting in the bag. Once the flavor passes internal panels, the next phase is consumer testing. In select cities, Doritos organizes blind taste tests, sometimes with up to 500 participants per flavor. Reactions are scored not only on flavor, but on memorability, uniqueness, and potential repeat purchase behavior. Statistical modeling software crunches this data to identify the most promising formulas. When a flavor is approved, it must be scaled up to factory levels without losing its integrity. Seasoning blends are manufactured in industrial blenders, often in batches of hundreds of kilograms. The bulk seasoning is tested for particle size, uniformity, moisture absorption, and flow behavior. During this phase, the seasoning is often reformulated slightly for stability, color consistency, and performance under high-speed drum tumbling. Then come the pilot runs. a limited quantity of chips is produced on a full-scale Doritos line using the new flavor. This lets engineers monitor how the seasoning behaves under actual production conditions, how well it sticks to the chip, whether it builds up on machinery, how the oil in the powder affects packaging line sensors. If issues arise, tweaks are made not just to the formula, but to the machinery settings as well. Finally, once all checks are passed, the new flavor enters full production, often accompanied by bold marketing campaigns and timed releases. Global coordination ensures that ingredients meet regional compliance, and new flavors often debut in test markets before rolling out broadly. These launches are tracked in real time, and consumer response loops back into the development pipeline, influencing which flavors stay, evolve, or disappear. This highly coordinated, scientific, and iterative approach allows Doritos to launch daring new flavors while maintaining the consistency and production efficiency that a global brand demands. Each new taste starts with creativity, but ends in finely tuned, factory-scale execution.